right now.
That's easy, you can get that. It'll play that computer. So let me go talk to Mark.
All right. There, now you're entered.
I suppose you don't know the password, right? That's what I'm beginning.
No.
Oh, yes, I have it right here. Go. That means you requested the tech tour on Tuesday, and hence you also have a yellow, right here. Okay. So it's color coded, and so that way we know who's supposed to go what day.
So a group will go Tuesday, a group will go Wednesday.
Yes.
I forgot my badge. We start at 9.
Yes.
See, Mark Barnes has got it for us. He's waiting for Sue to come in before 9:30. If he doesn't, he'll use his luck. So
Oh, we got
Just
nine,
nine.
and you
Still
know
nine.
that. Okay,
yeah.
okay, good. Good. Who's Mark Barnes? He's the contractor?
Mark Barnes is,
He's in the last office on the right, just before you go out the door.
he's the one that's going to invoice us for our rooms. I think we paid the guy right before him, but he's the one that's doing invoices now for our rooms.
Same person as last year?
Within one office of, yeah, he's.
Okay, then I probably met him then.
Yeah. Jessica retired or went off to greener pastures or something. She was doing the kid thing.
Oh, and you look at that, they have a popcorn.
It is a popcorn machine.
look at that, that's where we keep all our SARA supplies. We didn't know about that. We have SARA supplies in here, that's where you store them?
Just a couple overnight stuff I
Okay.
usually leave sitting out on the counter during the day. I just didn't put them out yet.
Okay. No, it's a good storage room. Right? It's a good storage room, so you don't have to carry everything back.
Yeah, I discovered it last year, found out it wasn't locked. I said, oh, really, I don't have to carry everything back and forth every day.
Oh, there's 2 popcorn machines. All right.
Yes, it's the ultimate in popcorn experience.
Have you seen our keynote speaker?
That is the sore subject for me. No, I have not.
No, I saw him come up in the dormitory last night.
You did good, so he is alive.
Yeah, I recognize him from the face.
Thank you. That was about to freak me out because it's like I have hair there and,
I believe that's him.
yeah, it's probably him. And, but he got his key because I left him the key, but that made him to be able to escape, so he didn't associate with this. I don't, it's like, I would like him at least to show up for a meal or something, so we could ask some questions. Because it's called the Charles Arthur Commercial. At least you've seen him. I haven't.
Yeah,
So I might disappear in your section and go bang on his door and say, are you gonna wake up and did he show up? Crazy man. Not crazy, I just.
They should have a clock in here.
It's right there.
Right where? Oh, okay. I can't see
It's
it.
there for them to see, but
It's for the speaker to see,
Yeah.
not for me.
I'm glad you reminded me of it. I've only got my watch. freaked me out because I've got whatever that alarm is online.
Easing into this. So I was gonna use, I can use my credentials if you want.
Yeah. Oh, okay, great.
Yeah, this is Mark.
Yeah.
This is the guy that you can see about the room.
Okay.
He's the big one.
So what, well, besides getting it set up, I need an internet access, you can do that too?
I could just log on, I suppose.
Yeah, because I'm going to use
Do
it.
you have it up? Or
No, I don't know how to use it. I mean, I have my thumb drive for my presentation, but a lot of it's based on the internet. Once we're logged in, do we stay logged in or does it time out?
I have no idea.
I remember I thought it stayed on last year. So, what's the weekend did her magic? That's a Great Lakes program. Is it Cheryl?
Ah, you're a fan, huh?
Yes. I talked to Jill, was the two guys that had died. Foundation. Yeah. She went down the he did a prayer.
Well, we're attempting to.
Oh, man. Families did all that. He did a prayer.
So your field of view on the camera, is it centered on the screen?
And we're not checking that now, and make some markers.
Oh, because you need the same thing, you need it on.
Oh, but I mean, he
He just needs to-
he wasn't doing any collecting. He was more precise.
I'm not sure how to switch users on that. Put my password in. Sue's already on there, so I'll come back.
She gonna be in before
I have
9:30?
no idea. We'll get it figured out one way or another.
Oh, okay.
So you took that.
Mark, what's your extension?
2227.
Now I got a network, I'd like to see some more.
3 2s? 2227?
What is that? Actually, I have it in my phone.
So we aren't up and running.
Okay, he's chasing it.
I guess,
If we
yeah.
had a long cable, you could plug in switches. Really long cable.
Where do you get your internet? Chip, where do you get your internet? Are you on
Where?
right there? So if we get a wire to go between over there, then we might solve it. If we got a hub.
Well, I have a router, a switch, so I have a port.
Yeah.
So run cable to this switch, it doesn't work.
Oh, maybe one of these closer to the podium has internet.
This one, I tried yesterday, it didn't work.
Didn't work?
But I don't know, maybe it was. Okay, I tried this.
But if we can't, can we turn on the screen, or we don't even know how to do that?
Which screen?
The projector.
I got that, that's easy. Easy, that's easy. Fix that. That was over here. It's on that. You go right here. Your system power, sir?
Thank
Come
you.
on.
Because I assume Ed will put his laptop up. And we can't really switch mine because we're dependent on the,
No, you can switch between.
I mean, we
You can
can't
switch between this one and
we can't make mine bigger because the next thing needs the keynote, so it's not like, all right, we'll worry about it.
So it's still computer, desktop. You turn green. So it should be desktop.
So we can't go beyond this point, other than yes.
Basically,
That's not here, that's not.
take a load and drop that.
Yeah, I walked that way. I tried to get back.
That's a good year. So I was trying to get to one of the places up front.
Okay.
Yeah.
We're trying to get this thing up. We don't have much time.
Yeah.
It is.
Don't stand.
Just stay. If you go outside, right, you're afraid you're.
I think it went from.
I mean, we get, if Ed comes with his laptop, we have that, but I don't know anything.
Okay, whenever you're ready, we'll go all around.
How long is, how long is yours?
We have about 40
I was stuck. Yeah.
Ed, have your laptop?
Yes.
Hey, yeah, you'll have a lot in here, really big.
You would think.
I'm not on it, because I've got too many projects going on. You're not through, Mike doesn't mind the attendance for you all the time, she's got her projects all over the car too, so. Mutual agreement.
Somebody's working on the internet connection, but if we don't have it, this is the backup. That's the plan. This guy is.
Okay, thanks, Tom.
Yeah, no, I do.
Great. Signed in for the internet.
Always come back.
I don't know.
It's working out that way.
That's what it is.
This is when you turn them off. Once you're logged in, is it? Where is it secure? This is
A lot of these things are
Yeah, I know, Mike, starts with a 18-hour drive up here. Across 2 days.
You have a long
Oh, right, yeah. I'm not a big, yeah.
That's what you're supposed to be, you go up to the top of the horn. Yeah.
all of that astronomy.
Yeah.
It should be, all of the.
I'm sorry?
It's good to build a probably should have.
I don't know, but Andrew rules, I
Yeah, it's just
know
like
my
this.
front camera. I got my camera, I know, anything in the pretty, that's what I got to roll.
Well, I have the sections slide, but really, it needs the internet connection. It's just kind of like, I guess, for the SARA website.
Now, we don't get to do this every time.
Either.
So let's use it how cool make that. Do it. Way back.
We need this anyway, because
He would take that. Carefully unroll the.
Internet today,
so we'll just roll it from.
Place where the curbs are all.
Can't have
Register. Well, that
for
could
some reason, before people got
So,
this stuff, my dad.
The problem is the storage level is very. Oh, yeah.
Yeah.
So you can hyper it, when you use it, you develop it.
So, right, like that's on the edge.
You know, the properties of it when it flies out and it absorbs the heat.
Last time.
Yeah, we got about 350 members. But
You said
that's a
the
lot of time.
flip switches here?
So about 200 a year.
I don't see that flip switch.
It's top.
Oh, okay. So let's try that.
Sorry?
It's on this.
That's it. Every number in there, they'll have all the
You hook it up with that?
I had a spare metal rock. Well, I learned something from an experiment, so it's a good experiment. I flew up in the backyard, it was like, all the neighbors coming out of the house, and my mom goes off to the guy behind, she finally talks about it, called. Yeah. Also, when you're, rock, it's very quick, like fire, one day has to be food, you would fire. Which one here?
It's gonna be,
So it was fire. Yeah, we make a lot of levers at that time. Where is that?
as soon as you hit that, it will be out there. And then, so, just make sure that's still working. Get there, right.
Make this piece of shrapnel.
They're gonna reboot his computer. No, it just popped up with the IT wants to do all the software updates. The answer is no. Well, you may not get that choice. You have to find Mark to log back in.
Yeah, then we have to find him and get him log back in.
No, I'm talking about, because yours starts at 1:30. Yeah. I'm sorry, that's scheduled.
I won't change my video.
Oh, yes, here it is. No, it's there. No, I was just looking at it. Hold on.
When you start talking, keynote speaker.
I know this doesn't always be
nozzle area. Put that, when you cast it in the motor with a, because it's such a very castable, you got a big rod out there on my gas leg, which is now in my shop. And it's a tapered rod that we grease very well, put it in the middle for the fuel down there. And then it's like, it's like rod, kind of taper, and they very smooth. But that's important, use for strike anywhere, make strike anywhere, you don't want to break. But anyway, so we take that on my cameras. Yeah, got something set up, got a mile and a half or something like that. And we found a place out in the middle of nowhere where the fire was on the church. I got another power for in the car. Right, that's what I got to go.
This is projector stuff. I know. I'm trying to figure out how to get
calls we shut down.
Yeah, but I've also noticed that. Even when it's real, it doesn't reset.
Warriors got involved, but all of us. Almost never surrendered that from the 15 to 19. Rocket car, right, killed an ass.
We have another last one. Oh, you're just gonna read?
No, I'm just going to read.
No, I would never do that to you. You know, one of the,
If now since the council,
the quality goes in before the name goes forward. Those pictures you never want. Give me about, we're a little late, give me 2 more minutes. Actually, I can, why don't you start? Or the cats, actually it's cats. I wouldn't start until slightly over. Humidity is so much.
Ladies and gentlemen, let's try to start this up. I'm Adrian Howell, Mr. VP. I'll introduce the other guy in just a minute. Welcome to Pocahontas County. Welcome to the biggest telescope in Pocahontas County. And they're real proud of it.
Size doesn't matter?
I'm not going there, you can't. There has been some in news, and I got paper clipping over there this week. The National Science Foundation chose Alternative A, which is good because it basically keeps the exact same thing they've been doing here at GBO, which is it's called GBO now, since they basically got splintered off from NRAO. And Alternative A is they're going to accept funding from external sources like the Breakthrough Listen Project, and still try to find some external sources of funding, but they get reduced funding from the National Science Foundation. So they're going to continue. I'm going to try to have Mike Holstein, the business manager, talk to us on Tuesday, give us a 5-minute, like he did the other year, how we're doing, how they're not doing, any issues. But that's a real good decision, I believe, and I think a lot of people here are happy because they had a couple of options. They could reduce staff, they could do some things, they could mothball the facility, and option D was to demolition everything. So, as stupid as that may sound, it was an option from some government committee. And there's 272 pages on the impact study. If you really are bored, I couldn't sleep last night, and I tried to read some of it. No, it didn't. But
Who writes this stuff anyway?
At the very end of the hall, on this hall down here, past the bathrooms, the very last gentleman is Mark Barnes. It's the very last door. Mark is the guy that gets the invoices for your room. Please pay your room before you leave, because then you won't have paid and we'll be in trouble. So he'll have invoices later this afternoon. I believe you pay the gentleman right before him, and he'll take a credit card or a form of payment. But just settle up with them and make sure he knows how many days you really stayed if you ventured off of what you did plan. We are still missing our conference books. I apologize for that, but I think they were stuck at the printers. Gary Memory is waiting for it. I have not got an update on him this morning on email, but they should be here this afternoon. and we'll issue that, and I'll also give you the memory sticks. We've upgraded in the Western. We went from CDs to memory sticks, as everybody said, I can't read the CD, so we got nice memory sticks with a SARA logo on it.
Adrian? Did they ever, I saw the question about how to mail memory sticks cheaply.
I don't think so.
I don't remember that one, but yeah. It used to be you could use media mail.
What's the question?
Mailing memory sticks.
I found out that if I put them in a small 4x8 bubble padded envelope, the post office will take them for two stamps.
Great.
There you go.
Good job.
And I've got the journal, I put the journal in there, and I was nice and put the conference proceedings from the last conference, which was the Western. I'll talk about that a little later. It was a very interesting event. We had some guests from Colorado, and they were very gracious. It turned out to be I hate to say the word better than expected, but I'll talk about that. It really impressed me with what they had there. Chip is live streaming this. He's got some comments about.
Yes, as every year, we are streaming this live on a YouTube channel, so everything that happens here is live. We have also the viewers on YouTube channel. There is a delay of about, I just measured about 15-20 seconds between what's real here and what's on the YouTube channel. One comment is, please try to avoid to mess with that camera there. Don't shake it. It's pointing to this area. Second is that presenters should move pretty much between that red line and that other dashed red line to be inside the tray. Yeah. The third comment is about audio. Because we have two microphones which are located on this side of this room. The microphones are picking the noise or the presentation. But you may not know that you are live if you are talking. So please try to understand that people online can listen to you. And not only that, but it's also recorded. So you don't want to be on file with some
No colorful metaphor.
And the last comment is for present.
I'll just say that last year's SARA conference has a whole bunch of stuff, and I learned from painful experience. Yeah, so if you're telling a life story, just think before.
Sanitizing.
Okay, the last thing is questions. Some viewers online may have questions like everyone in this room. So if the presenters will allow them to ask a question, I will relay the chat text question from here to the presenter, and the answer will come delayed 15 seconds back. So I hope that will work. But just give them a chance to ask questions if there is any. That's all.
I was going to make a comment to that, Chip, is you have to be very careful, as I learned a couple of years ago, that when you're doing something, if there is anything in the background, make sure whatever in the background, noise-wise, is also sanitized. Because I didn't realize that I had some music playing in the background, but guess what? Music is copyrighted. And they were on Chip, like right on rice. It was, even if it's totally unintentional.
Well, it comes time I need to introduce you to Mr. Redcap. He's our illustrious president. Where is it? Right here. This right here. Okay. This next thing is, if you can't remember his name, look at the object on his head, and it's red and it's a cap. So that's good. And according to the rumors that everybody's heard, it is true. Where is it? You took it off. Where's your jacket?
Oh, it's too hot for that. I'm sorry.
Here's his jacket. His jacket he's been wearing the whole time came from his mother-in-law. Okay? So it is true. So, take it away, Ken.
I was going to say this humidity for us Michigan boys is still too much. The first thing I wanted to touch on real quick, because I passed Mike in the hallway as well, the business manager for Green Bank. And I found out, I'm hearing somewhere between 3 to 5 years they have funding. And I said, we'd really love to keep coming back. And he was delighted with that, he's happy with that. The other thing, though, that I wanted to deal with is I'm kind of liking August. So I want you folks to be thinking, if you like coming at this time of the year instead of June, July, it's a little more crazy with the star parties, I'm hoping we can repeat that and just keep coming back the first week of August. But if anybody has any issues with that, please let us know.
So that's going to be a guess of NRAO or National Science Foundation, whatever. It seems like we should probably fit whenever fits best with them.
Well, that's why August works so well, it fits well with them.
If August is better for them,
Because-
of August.
Well, June, July, they're having all of their star parties, and you know how much fun it is when you've got 50, 60 kids running around this place, and they're all out of rooms. I mean, this time we didn't have that issue. I believe we got everybody rooms this year, so that was a plus. So just wanted to bring that up. That's the way I'm leaning. I did one other item. I talked with David for a little bit about Western next year. And hey, David, can I say tentatively, or it's very loose, VLA, or?
Very loose. I haven't talked to the director yet, and I don't know what he's going to say, so all I can guess, but I guess are worth the price of admission. So anyway.
That's what we're aiming for.
Yes. So I'm guessing what happened is to Carl, but this is always subject to change if something goes wrong, so we'll see what happens.
So it's not cast in stone, I'm just simply saying that's where we would like to go if we can, yes.
Yes.
Any guesses on the dates?
No, well, it'll probably be in late March.
Yeah, there you go, yeah. I mean, we just came back from NCAR, lovely facility, had a great time. Hope to be back there. That was our first time, I believe, in Colorado, in Boulder.
Yes, it is.
So that was, and I really enjoyed the keynote. Was interesting. He talked about the sun and the repeatability, which that really kind of caught my eye, and my ear. Just the fact that he was almost like saying you could buy, natural gas futures based on. It's like, and hey, math usually doesn't lie. So, also you'll notice in the back we've got the tents set up behind the dormitories. So I'm hoping, I'd really like to make sure we get some of the younger attenders and the older attenders to help the younger attenders. We have power, we have internet. Right now we have 2 canopies and 2 tables. I'm mulling over the fact of having possibly 3 tables and 3 canopies for next year, because it really works well with the weather if it decides to go south on us. So that, let's see. Oh, yes. This year we started using a software package called Blue Jeans. We're using it for our teleconferencing, which I'm really delighted. The price is reasonable. The quality was there. We tested it out a week or 2 ago. It was wonderful. They have an app. I don't know if they have, do they have an Android app? Okay, because I have an iPhone and I loaded it onto my iPhone and it worked perfectly, that app. So there is a Android app for the Blue Jeans. And the Blue Jeans is really inexpensive. If there was a need for like a group within SARA that needed to use it, just reach out, I think, to either Chip or myself, and we'll get you the information so that you can use it. It handles up to 50 people. So I don't know of any meeting that we have that exceeds that amount. And with the, I'd say, what do we have, about 10, 15 when we tested it? And
10.
Yeah, 10. And it was really, there was no issues. I don't think any of the participants had any problems with it. So that's a step up. The next step is I really want to see what it would take for us. And kudos to Chip for setting it up and getting it working. But I would like Sarah to actually own that capability and then that video streaming. Because I know that there's not a ton of people, but there's a number of people who like to call in when we have our meetings, we have our conferences. So, okay, so we talked about SARA West, we talked about SARA East, and one other thing I wanted to touch on, being the president, I have not taken full utilization of committees. And I hope to change this year because, quite frankly, all of the different things, you know, the vice president taking care of the conferences and the president taking care of his stuff, why not spread the wealth as far as helping so that we're not stressing people out? And that's just a point I wanted to make, something that I've been lax on, and I apologize. But I'd like to start pulling more people in to help. And if anything, just to train them and cultivate future presidents and future vice presidents, etc. So, and I'll just end with this. I was tickled to hear that GBT did get funding, because I would really hate to see this facility go away, because especially for a group like ours, it's perfect. And the people have been wonderful, and it's just been really great. And as a matter of fact, as somebody pointed out, the staff here actually looks forward to us coming. So I hope we can keep that up. That's just a wonderful thing. You know, they're coming. You know, no, they look forward to us. We try to treat them all. They treat us. So without further ado, Adrian, are you going to introduce the next speaker or the first speaker?
Yes.
Thank you.
We've got among us a gentleman who works in D.C., and he does a lot of radio astronomy when the government's in sequestration. And you learned that last night. We've got Steve Zekas. He does all of our sessions, and so he's going to update us on that. So last night he was very productive for 27 days or something like that.
25 days shut down.
35 days.
So this is the first time slot after the announcements. I do the SARA section updates. And this morning we have an internet connection at the podium, so that's good. I can show you actually go into the SARA sections as well as the 20-meter Skynet site. Yesterday we couldn't do that. We made the 20-meter dish move, but we couldn't actually go to the site on the screen because we didn't have an internet connection up here. So this toggle is a little tricky. So what I think I'm going to do first is go through the 7 slides I have up here first, just briefly go through them, and then just go to the internet connection to the items I'm discussing up here. So the SARA sections were created a few years ago. It was to make the SARA website look similar to other amateur and professional websites. If you go to professional websites, they usually have subsections in there, different topics of interest where people interested in those topics can go and share ideas with fellow colleagues of the same interest. And it makes volunteering for those activities a lot easier. So that was the purpose among them, and we're trying to populate them a little bit every year. So if you have ideas, please let us know. If you're working on personal projects of interest, and you've got some conclusions and results that can help other people observe the same thing, we can post them on the website. So. So, I mentioned it was to organize SARA, like other websites. A lot of the documents we post, they're living documents. Somebody might start something, take it to their limit of ability, and someone else may come along later and update them. There's a lot of information sources for things that we can post. things like protocols. SARA has an active listserv. All those conversations are archived, so there's a lot of great information there if you want to put together a protocol based on the top of those listservs. There's a small SARA section team, which is great to have, just to bounce ideas off of. There's examples of things we've done in the past, like observing protocols, data templates. I'll just show you that once I get into the SARA section. And so I mentioned a little bit about volunteering. There's a lot of things you can do. This whole presentation is on the SARA section website. It stays up for a year with a few other things until I do another update next year. There are 6 sections. So starting from the Earth, we have solar systems, stellar section, and then galactic, and then we have an instrumentation section, an analytical section, and an outreach section. So 3 of the section coordinators are here today. I do the analytical, Skip does the stellar, and Dave does the galactic. And in addition to the sections, we have some other interesting tabs on the overall SARA website. John Wallace has a good education page. The management section is very interesting. I find a lot of good policy there, and the SARA sections, how they're operated, is placed there. So that's worth looking at too, especially if you're an officer of SARA. And once we get into the sections on the internet, I'm going to show some of the updates that we have. I'm working on updating the mission statements, so they're not listed yet, but I'll get them out in the near future. If you're here yesterday evening, we did the 20-meter dish demo, and then I talked afterwards about the SARA observing project. So we'll look at that a little bit. And the research paper on that is at that meeting. Not for the SARA effort, but the effort is based on that. You have a guide to look at this paper. So let's go to sections. That's why I didn't want to go back and forth. Thinking, you know, hopefully we won't have to reset the whole thing. So that's the problem. We need someone walking in. Mike Arms. Did someone reach it? Where is Adrian? It's at the end of the hall.
I think you can just go to the control room, to the phone dial 2227. 2227.
Trying to mark 1, 2, 3.
Yeah, get him walked out. Yeah, get him walked out. Go ahead.
Yeah. Hopefully that will get him walked out.
So once we get into the SARA section, some of the things that we're going to look at, I'll show you where all the presentations were presented.
It's on its way.
Okay. I'll show you an example of a protocol. We've got the SARA flyers on the outreach section that are useful if you're doing outreach work or just new to SARA and want to read up on it. At the end of a lot of sections, we have different types of awards you can work towards. The Astronomical League has a Radio Astronomy Award. Put a new link into the ARF for the FCC licenses. So I may be the only internet user today, so this might not happen again, but you need to sign
Yeah,
in.
I'll be here all day. So,
Thank you.
sure.
All right, so let's look at the SARA main page, the top ribbon. You go all the way to the right. There are the sections. And what we want to do, we want to start off with the introduction tab. So some of the feedback we got in previous years was, if you're new to radio astronomy, what do you start out with? So this beginners tab was some basic information for beginners to look at and start reading. If I'm not mistaken, Ed, I think your introduction to radio astronomy is on this beginners tab as well.
I think it's up on the top menu. Keep going up.
I remember posting it a couple of years ago.
Yeah.
Education section,
Yep.
so that's John.
That's where it
Walsh's.
is.
Okay,
That one's a little old. I need to sit down and refresh it.
okay, so if you were here yesterday and wanted to get a copy of that, that's where you find that.
Yeah, that's the version from about 5 years ago, 4 or 5 years ago.
So on the analytical section, the stuff on the CASA PAA observation project is here. That update I just did, the 7 slides, that's this one, what you saw yesterday there, the 60 slides, that's right here. And once you get into the 20-meter scope site, there's some guidance there for you. How to operate the scope, and then how to interpret some of the results, and how to calculate a CASA flux value. There's a article here just describing the CASA program in general. And then this here are some guidelines, more for management, but there's 2 ways to get into the Skynet account. So if you're here yesterday, the whiteboard, that's not on the screen because that is just for observers here. You'll log in as SARA, and then you'll type in the password, and that'll get you in there. There's really no restrictions on that. You can go, you can do some experiments, move the dish, you can see that move outside. All we ask is don't eat up the time in there with raster scans, which take about 30 minutes or so. I'm going to go to the side, I'm going to show you some of the examples of where to look at previous submissions so you can get an idea of what a raster scan looks like. If your first day is today, we're live streaming, you want access to the account, just email me. My name is up here. Now the SARA account, that's a little different. That was created recently when the NSF had some additional guidelines. You need to be a U.S. citizen and state that in an email to me, and also what you're going to be using it for and not using it for. So look at those guidelines, or if you're interested, just email me and I'll tell you what they are, and I can give you the password for that. And those guidelines are right here. One of the presentations we saw yesterday, Charles Osborne observational tips, that's right here. Those were very useful. The CAS-A research paper that was done by Dr. Reichardt on the 20 meter and the 40 foot. Because some of the 40 foot data was used, or can be used for this program, I had skipped attached some notes here, the 40-foot telescope calibration examples. So if you're planning to use the 40-foot scope, you might want to look at this. That might be useful to you. if you scroll down on the, here's one. I mentioned about a protocol. This was just put together by, one of our members sent me a, oh, there it is. Wolfgang Hermann in Germany sent me about 20 links for radio occultations on the internet, different papers. So I read them, kind of distilled them into a document here. So that's what a protocol looks like. That's where I got my information for this. And they're quite difficult to do, but if you're interested in that sort of things, that's what it is. Just distill a lot of information. And I haven't looked at this in a while, but I believe there's a timetable in here too, which is one of them. That was one of the things we talked about yesterday. So someone asked about protocols or developing them, so that's why I brought this example up. I thought I had an upcoming calendar in here. There's not too many of them. We can take a look at that. Did someone, Ed, can you write?
Top right.
Top right?
Yep. Internet
Oh,
Explorer.
thank you. Here's the links to different radio astronomy awards. If you're new and want to learn, I think this is a great program. I went through it. There's 3 different levels. I learned a lot using some of the basic radio astronomy telescope programs, and the Super SID and radio meters, the 20 meters, and the IBT, the telescope. So that's a great place to start in radio astronomy. So I put this one in. This talks about FCC licenses. The exams are free. There's a technician, general, and amateur extra. As part of these licenses, there's a lot of radio technology that's discussed in the manuals. It comes in very useful. So yesterday at the 40-foot demo, there was some electronics discussion going on with Skip, and I was starting to understand some of the things he was talking about because the extra license covered a lot of that. So it's also, so this is a very good learning experience here. What they discuss is applicable in radio astronomy. And if you're interested, I thought this is a very good reference too. All the prior SARA journal articles are here. And a lot, and this one is by different sections. So if you got a particular interest, you can look up where these articles are, try to track them down. And the outreach. Here's 3 brochures that SARA typically uses at outreach, so they're very good learning experience as well as for people who do outreach. Print these. This one here for teachers is about SARA grants. So And we do get a lot of features at SARA outreach events, and the other two are more about the different types of basic radio telescope instrumentation and radio astronomy in general. Yesterday I had a chart up with the Inspire, Super Sig, Radio Jug, IBT, 20 meter. There's a couple more of these too, in the instrumentation thing. We added them. They were known in the SARA journal in the past, but we placed them there. The E-Callisto radio solar spectrometer network, that's a pretty good look at. It's a little more pricey than the 100 or 200 basic radio telescopes, but still fairly affordable. So that's something to consider, as well as the 3-axis magnetometer kit. I think I'm going to go to the Skynet site now, just to show you how that works. Skynet site, they also have some free university courses. I did them, they're very challenging. You get a certificate of completion at the end. But we want to log on to actual Skynet. So I'm using the information that's on the whiteboard to my left. Hopefully you're not going to see that on the live stream. So you've got the passwords for this if you like it and want to experiment with it more, just ask me for the other SARA account. I can list you down for that, just email me. All right, so this is what Adrian was doing at the back table yesterday. So the SARA account is just radio, but you can get optical too. So these were targets that were looked at in the past. You can see we have a lot of that balance, 75-19, that's seconds. We've got about 5 hours in there. So that's what we're saying, be mindful not to eat up to 5 hours with a few raster scans, which takes 30 minutes. Most observations just take a few seconds. 10 seconds is plenty of time, so you can do a lot that way. Let's take a look at one of these observations. I'm not going to put a new observation in, but I just wanted to point out where we get some of the information on it there. So if you're curious to see what they look like, let's just pick one of these. And hopefully they were get to look at the data. So this says this was the SARA observer. If you want to log of all 20-meter observations done by anybody, you just press that.
It's working on it.
All right. And it's by year. I think it starts in 2013. I'm not sure when. But it's organized by year. And you can see what other people have. The quality varies a lot depending on if it was in a student experimenting or if it was a professional. But let's just take a look at, so PSR or PSC are usually pulsar, so let's take a look at one of these. So there's a lot of to learn here. I mean, using this telescope is quite easy. Interpreting and understanding, that's where the challenge comes in. But that's what you can look at. So you can do your own, but you can also see what other people have. let's see if I can find a source here. Looks like this might be a daisy. This is a, is this a daisy or a raster? Okay, so,
That's a raster.
okay, I'm looking at it here as if it was the daisy petals. But no, it looks like a raster.
Or your bottom one.
So here you can actually see the image of the object because it's sweeping back and forth the area of the sky. And that's why it takes up a lot of seconds of credit. But this is on top where you go to get the raw credit. This gives you information about the input parameters that you would input. And then here's the raw data. This one is showing continuum and spectra, what we looked at last night to get the flux value of Cas A. That was the Kelvin count, so I'll try to get one that was tracked. And then you can switch different modes. If you press that, you get a different image of what it looks like. So, in your different views. So it's a great learning tool.
Steve, can you back that pulsar data set?
Pulsar?
The one you showed there with the pulsar back. There's a whole different data set. The graphs from gray and white.
I'm trying to,
Just click on blog over there.
okay, yeah, that will.
I'm looking for the observation ID number for that.
I haven't gotten into pulsars, so I can't answer too many questions about it, but
Yeah, it looks
there is a
like
special pulsar mode for 20 meters.
That is not a
58,680.
No.
That's not a good pulsar.
So go back to.
As I said, the quality varies a lot depending if it's in a student or somebody else experimenting or. And there is something called a pulsar search collaboratory. I think they're collecting information or something. It's just, there's so many here, and they're all different qualities. Let me try to find the, I guess this is the one that's highlighted that I looked at, right?
It's one,
Yeah, I'm trying to find
it's not a pulsar.
That's not a pulsar.
Yeah, so again, the quality varies a lot. If you look at a few of these, you will find some good ones. So let me see if I can pick up something that was tracked,
from the Skynet.
because I wanted to show you the Kelvin data too.
From the Skynet portal, you can plug in the observation ID if you know it, and that'll pull it right up. Should take
Oh, you mean the Novak? What, I'm sorry, what did you say?
On the main portal page for radio observations on Skynet's portal, you should be able to do a search on your observation ID.
Okay.
Skynet assigns the observation ID.
How do I get back to it?
Where are you trying to go?
To the main page, and it's not taking me back.
Yeah, that's not Skynet's site, that's NRA's site.
Yeah.
I'd have to log back in then, I think.
Yeah, I think maybe.
So let me just,
I will go get it.
Right below you there, Skynet MyObs. Go back to the page you were on. So right below where the log click, where you click for the log, down to the left. Whoop, too far.
oh,
Under latest, then log, then
Skynet MyObs. There you go.
okay.
There you go.
That's
Oh, thank you. What did you want to search for?
You could probably put in the observation ID number and get that. So, viewer review.
Where's the search box?
I'm looking.
Can you recall?
think if you go to my observatory.
Yeah.
Where's that?
Top point navigation, my observatory.
My observatory,
Right
radio, okay. There's a search
Go
box.
in
You remember what that was?
58560.
58560. Now, this just searches
I don't know.
those on the particular account. It won't go into the major log.
Right, okay, so your observation IDs are there on the left in orange. Okay.
That's right, those are done by the SARA account. It won't take the whole log.
That's Skynet generates that. So does that help get to the log you were showing with all the data, all the different observations on it?
Well, that we went into, and you just wanted to go back to the one I pulled up first, right?
Yeah, I mean, compared to the optical observation stuff, you get, one element maybe per observation ID number, and that screen you were just showing had like tons under 58560. I just know from looking at the URL for this, that that's the observation ID number that's in there. So I'm trying to get from where you were with that over to the 20-meter site that's here, and how you look at all these different runs for that one particular observation ID number. You know what I'm saying? Hit submit there, see what happens.
Hit what? So submit.
Yeah, it doesn't.
So nobody did that here at SARA. That's why it won't go to the log.
Must be somebody else's observation.
Yeah, that search box is only for the account. So if you want to look at, in general, what people use, there's not really a way to search it.
There is, it's buried. You need to read through the way I use this is there's a file on there called observing advice, and if you start there, there's links off to other places. One of them will take you to a search box on the results page. That log page that's got all, that big long list of FTP things, there's a way to search that.
So the way I found Dr. Reichardt's data was, he gave me the years, he gave me the number, and I just scrolled down the list and found it. And then I opened it up and confirmed, yes, it was his.
Yeah.
All right. I'm
It's,
sorry to keep asking these questions, but where did you get that list and stuff?
that was from his paper. So on the 7 slides I showed at the beginning of this, I listed his link. That link for his paper, which is on the internet, is in a lot of places. It's also in my slide deck from yesterday.
Yeah.
So you can do a Google search, 2017, Fading of Cas-A, Dr. Reichardt, and it's a very good paper.
So you can get that whole list of different observations? once
Yes,
you get
it's in
this-
his paper.
once
That's
you
how I
get
found
That
it.
was my question. Okay, good, thanks.
And then his paper has a lot of other useful references, including the PhD thesis that was used to do the statistical and analysis and fit testing. Let me see if I can find something that's tracked here. Let's look at this. What I'm trying to find is, it depends how you set up the parameters, but I wanted to show an example of what the Kelvin data looks like, but I keep getting. Let me see.
Yeah, I think if you hit that calibrated, you can.
Yes, there you go. Here it is in Kelvin. So this is the, yesterday what I highlighted, cut and paste, I put into the Excel, reformatted, and then it did a search for the maximum temperature, Kelvin, which is how I found which is when I plugged into the formula for flux. So the Kelvin calibrated data is, that's better than the count data. It takes out some of the noise and other things. And there's a calibration run automatically done before the start of the observation.
And those observations, if you go back to that file, the observations that are calibrated there, in one of the columns, it's got a 1 if it's calibrated. So see that on the red line there, see the squiggly part at the top? That's where it's calibrating.
At the beginning and at the end.
Yeah.
Yes, that's what and it's kind of like a,
And you can see that in the data file.
You know, so, and you can, yeah, you can see that in the data file, so it's very,
You basically have a 9-degree Kelvin calibrator there, it looks like.
so you've got a lot of great data
I
there.
understand how it works, but there is a file with all the calibration information in it as well.
In addition to the links I provided yesterday in the demo, I believe this button here, this link, will take you to at least one of the sources for the logs. A lot of different things, including the calibration data that they did. So everything in my slides presentation yesterday, how to come up with those flux values, was derived from documents I found here.
Search projects, that's, I think that's where you can search for other people's observations.
All right, so there's a lot here. You can spend a lot of time looking. Yes?
Just a quick point, I just wanted to say, if somebody's using the 20 meter and they're wondering about something or other, I use the 20 meter here with an account that I have, and I use it for looking for RFI. So if anyone has any question about the data they're taking with the 20 meter, just contact me and I'll log in and I'll try to see if there's some noise bump or something you can explain, and try to track it down.
And you can get Skip's email. Just go to the Stellar section. He's the section coordinator. You'll find his email. You can reach him. And that 20 meter dish is not used a lot throughout the day. When you log on, there's a very good chance that your project will go, observation will go through quickly. Even with an event, when we had the 2017 solar eclipse, partial solar, not solar, yeah, solar eclipse, I went on it and I got data. And I used that data to write a short article for the Associated Lunar and Planetary Observer Journal. So it's pretty much on demand. The only time I couldn't use it immediately is when it was down for maintenance. That happens sometimes.
Is there any way in advance you could reserve a very specific spot of time? Like, let's say, you know, the moon is blocking a radio source as viewed from Green Bank, and you want to catch that occultation. You would
Probably
need a very
have to
specific
coordinate
time
with
slot.
someone here.
No, you can plug in the time you want.
On the
Skynet portal, you can put it
on
in.
the Skynet portal, you can specify a time that you want the observation to happen after.
Isn't, but if there's something important going on in the sky that researchers are going to look at,
Yeah,
I think they have the right to bump anything.
Yeah.
So I was kind of lucky with the solar eclipse.
Yes.
At least enough to get some data for it.
I don't imagine we're their highest priority users, so I think we're going to probably get bumped.
And part of the reason the Skynet account was set up for research, if fast radio bursts occur, they would use the optical scopes to try to hone in on that, so that would bump others. So it looks like my time is, one more question?
Just quickly, did you mention that sometimes the X band and sometimes the L band?
No, I haven't, but if you go on to the 20 meter, it's usually L band. And that's the only thing it'll give you a choice of, L band, and then you can do the hydrogen, OH, continuum, pulsar mode. Once in a while it has X band. If it doesn't last that long, it's maybe up for a couple weeks, but they do change the receivers on that, yes.
Yeah, I just real quick, there is a project underway, I've seen it across from where I sit here, which is to make the X to L automatic.
And you were telling me about that, so I was really
So if you
thrilled
do see
about
it
it.
in X band, I'm guessing a few months from now, there'll probably be a link somewhere so that you can switch it. You don't have to wait for them to go up there to the feed and switch out the feeds.
Okay, so, thank you. So you got the,
One other thing you're going to find when you get into it, you may want to take a shot of something that's not going to be at a good altitude until maybe, midnight, our time. Well, that's okay, you can factor that in, except that you have to put the time in GMT, whereas other times are shown local. So you have to make that conversion, and oh yeah, don't forget if you're in daylight time or standard time. So those are just another one of the little gotchas that you have to watch out for.
They modified it a little bit for when you go program your one, when you see that, you see a sine wave when it's visible, it now says hours from now.
Right.
And that's to kind of mitigate having to worry about, any of that stuff. You just figure where it's going to be in the location of the sky where you're observing from. And if you want to observe it at midnight here and it's 8 p.m., you just pick 4 hours from now to show that real time. It's a lot easier than it used to be. It used to be all that. You used to have to go
So maybe I,
bump back and forth for daylight savings time and all that stuff.
Dennis, I thought you were waving your hand to say I was out of time. So.
Well, you are, but.
But you reminded me of something. So one of the items on the SARA sections are those data templates. And it was brought up a few times yesterday that you want to share data from different radio scopes. You have to have some kind of quality control. So a few of us on the SARA section team put together these data templates as an attempt to, what is the type of information that we want to collect? So you see them on the different SARA section pages, but this is what they look like. So if you've got your own projects, this might be very useful to you, or if you see that there's stuff missing and you want to tell us about that, we can update this. But that was, and here's some notes. These were by Ed, and I didn't have time to incorporate them, so I just left them as is. Charles, so maybe that somebody else can volunteer for that, but I thought they were important notes, so I've left them there. So that's the living document approach. Something down and then add to it. Okay, so I think that's it. So thank you for your time then.
Appreciate it.
You've got cookies and drink and other stuff in the lobby. Supposed to be back here by 10:15. Let's try to be here sharp as our keynote speaker. He's going to discuss something that's very important. I'll let you disengage the work product. Yes.
I'm just every once in a while. Fix for my wife or other people. You know,
Well,
it's
in
not
those
a
virus
virus.
I don't use them anyway. Yeah, hopefully you got some
Yes,
techniques.
I have antivirus on here. I have all sorts of productivities on here.
That's what I figured.
For computer. His own, yeah, he's for computer. So, I'm assuming it should play no, it's already, yeah, it switched over to desktop. All my pieces, parts. Well, this guy's kind of
This guy's been here before. Been here.
Been at this group.
Appreciate the time.
I'm glad it worked through 10, because sometimes
It's fine.
sections go too slow. Once we got at the, looking at the section, 20 meters, that 10 was the heat up. Especially we didn't have that yesterday. Yeah, well, oh, I can see they were no good. I didn't know it was good or not, I was just thinking of, so that's what you get. But there are some beautiful.
Oh, yes.
Just, you just have to scroll through and pick them out.
Yeah.
So,
Okay. Yeah. I want to understand those lots more because they're obvious.
yes, that's the same thing I want to do. It looks like there's a lot of data, and you can use it for something.
Yeah.
And you just gotta find, and I think the quality one, besides scanning it and looking at what's actually good, that Pulsar collaboratory might be like this, so it's PSC and then the Pulsar.
Yeah, I think so. My ears are.
Oh, it's for the,
I know, but it's, you know. 10 minutes, so we got to start trying to start on time, so give you much.
we still have time?
Yeah, I got you, I need to swap.
Well, it could be that, I was actually thinking, it's mine, and I was just saying, I'm gonna throw it away if you want. But I guess for the bill prices, we could do that, whatever's left over. I haven't used this in yet, this is maybe switch for 3G,
Oh, it's calculated.
Yeah,
Why?
it's ready to go. You just have to connect to.
Is it commercial made or?
Yeah, I bought it, I just haven't used it.
So it's okay?
Yeah, I believe so. That's just an extra. You know, power strip. That's it. I need power strips. I don't get it. Right, originally I thought about giving it away, but I figured we didn't have all the door prizes, so I picked through it, what's not, clean like these. It's just access for, those cables that don't break. But I have not heard from and they explain everything. They have to cut back. I know my wife can see oh yeah, oh, he's still active, he just doesn't, he's a traveling. Maybe he does, or he just. It's huge. It's a freaking man. I mean, I've actually been looking for it for time because I'm looking at this. It's bigger than, it's almost bigger than my car. We just don't get a lot of room, so we have like 700 square feet. Yeah. Oh, yeah, I'm not looking for I just, yes, it's, I've been watching, and one of the things that they talked about is this is some things. It's like having a huge home and you only use a quarter.
Houses are like, as much as you buy, as much as you have.
That's where I think that's what that is. That's on the phones, or that's on music.
I'm not following you around.
No, I'm just trying to figure out, seeing what there's. So what does Patrick do for a living? I get paid to do this. Well, I'm automotive, I work for a brake company. That's what it pays for. It's on the Oh, that would make sense. There's a fee more for.
Yeah, so.
I was sure because when they did, I think it was Super Bowl II. It was the one where they went around and moved several visits in. The bad guys heard, or no, they measured the Houston. So every time I hear Houston, so you're it's the usual, or did you get explained about that?
No.
Don't forget because we So, and the other thing, I don't know if you heard that. I didn't know. Because it's like, I'm gonna have a friend that actually church, and he's like me, there's one really good option out here before we really realize what we're doing.
Perfect thing for
No color you
That's the part of the lecture about how you username and password.
Oh, we could have, before we break for lunch, I'll have, was it, probably Adrian, or you can go right to Adrian.
Okay.
Just go to Adrian.
2 hours.
It's pretty straightforward.
I'm sure there's a trick or two to it.
No, I actually think it's kind of a board when you walk into that room, but
Okay.
because there's nothing to get out of the network in the room. That's just go.
So, but from home, you need to know some things.
Well, at home, I have to log on to my
Yeah.
work
Password and.
But here you go, I haven't, so once I connect, I just go to the line.
And it was worse. So that was one of those.
What was hard
Oh,
to predict, it's how bad it was going to be.
I would like to go at least.
I mean, in terms of
Everybody comes in.
Yeah, that's good. So they could be spread.
Yeah, you guys, you know,
email
Steve
It doesn't vary as much as I thought. It's like 15. It's very much more reason for that. Plenty of people were always
All right, then you got to go. You have to leave. So you'll
Yeah, me and yours
but really appreciate skill at a time. If you have some time. Yeah.
click here, all of a sudden,
Also moved.
moving target. Switch tomorrow.
We'll have to make a choice.
Is that how it's a Thursday? Pushing the hour Sunday.
make sure it's
Not Friday.
It's like there's some
We just couldn't try to.
4:32.
Look at the camera.
What I was doing, I was thinking, to my son, my husband, also do that. Because that's what I'm looking for, people that have stuff.
Either one.
That one has less restrictions.
No, the operation.
Yeah, they're both, yeah. Because GPO pays for that, we just kind of let people experiment first time without it. But if you want to use it more.
Okay, guys, and ladies, sure. The current census is there's a 1 in 4,000 chance that a space object greater than a kilometer is supposed to hit us. So I don't know who's counting and how many years it will be, but 1 in 4,000 is not too good odds for me because you don't know when they're coming. But the story was I was at a Chick-fil-A watching the grandkid play. I think it was spaceweather.com. Dr. Tony Phillips has a real excellent website about everything. A lot of sun and a lot of CMEs. And he was mentioning something about planetary radar. And Dr. Taylor, I think, was a little name popped up. So I just searched him. When I saw his resume, I went, this is a great keynote speaker. So you can get stuff done while you're watching the grandkids. On his email signature, he says he's a defender of the planet. And you'll understand a little bit later what that means. He has 9 years of planetary radar experience in Arecibo when he first started in Puerto Rico. He uses planetary radar to constrain the orbits of near-Earth objects. He can define the shape, the size, and densities of the object. He's showed that even sunlight can change the rotational period of an object. He got his PhD from Cornell, and he's currently the leader of SARA planetary radar and the planetary radar defense group in Houston, Texas. So kind of scary when you are responsible for defining what's fixing to smack us. So I'm going to let him tell us how that works.
Here's my entire introduction. But yeah, as Adrian said, I did my grad studies at Cornell University in New York. I graduated with a PhD in astronomy in 2009. From there, I moved down to Arecibo Observatory in Puerto Rico as a postdoc and got stuck there and never left. Well, I eventually left, but I was down there for 9 years. I eventually was the head of planetary radar at Arecibo Observatory. And then just a year ago, I decided to leave Puerto Rico and move up to Houston, Texas, where I'm doing pretty much the same sort of things, but now in Texas instead of Puerto Rico, at a place called the Lunar and Planetary Institute. So, yeah, that's my story, so thank you. So yeah, the planetary radar is something that you don't really hear about that much, but it's an incredibly powerful technique in astronomy for studying really anything in the solar system within a reasonable distance, and we'll see that in a second. So, of course, there on my cover page is the superstructure of the Arecibo Observatory, and so a lot of what I'll be showing you is concentrating on work done at Arecibo because either I did it or was involved in it or heard a lot about it from the people I worked with. So a lot of it will be Arecibo related. So just a brief bit of history. The Arecibo Observatory was proposed back in the 50s by Bill Gordon at Cornell. And it was originally meant to be an atmospheric or ionospheric telescope. It was to study electron densities and temperatures in the ionosphere. And it was quickly realized, his original idea was to have this enormous 1,000-foot diameter parabolic, essentially transit telescope. It wouldn't move, it would just stare at the zenith and see what was happening in the atmosphere. And it was pointed out to him that with some modifications, you could use it for planetary radar and radio astronomy. So instead of using a parabolic dish, they turned it into a spherical reflector, and then they put a superstructure above it that could move so you could track things in altitude and azimuth. And that allowed you to do a lot more than the original plan and made it really attractive to try and build. So I note here that it wasn't just electron density and temperature in the ionosphere. They also wanted to look for, quote, transient streams of charged particles, which was a sort of failed way of saying Sputnik and ICBMs and things like that, looking for things that were causing trails of charged particles in the ionosphere. So they decided to build this telescope in Puerto Rico, and if your eyes are really good, you can actually see it in this map of Puerto Rico from, this is a picture from one of the space shuttles. Actually, if there's any chance we could turn the lights down really low, because a lot of the images I show are notoriously difficult to see in a bright room. Definitely not that one. So, oh, that'd be really good. Now everyone's going to fall asleep, though. We'll take our chances. I think it's worth it for the pretty pictures. So that's good.
Leave it be.
So, if your eyes haven't found it, there it is. There is the good telescope from space. So this is what it looked like before they built it. It was a tobacco farm in a sinkhole in a limestone karst topography. The government bought the land from the farmer, and then with a little bit of dynamite and some hard work, it turned into this. So there you have a 1,000-foot diameter dish. So you've got your 1,000-foot diameter dish here in the sinkhole, and you've got sort of about 500 feet up to the superstructure. You've got several hundred-foot tall towers here, concrete towers. In the end, this is about 900 tons of steel being suspended 500 feet in the air. And you can see a road going down to the bottom of the dish. That's actually underneath the dish. At this point, this was essentially chicken wire. It was just a metal mesh a couple centimeters across each of the little bits, because it doesn't matter if you have holes in your radio antenna as long as the holes are smaller than the wavelength that you care about. So they were working sort of below 1 gigahertz at this time, so you could get away with a dish made of essentially chicken wire. So that's how it lasted for about 15 years or so. Then they decided, well, if we make the dish a little bit more solid with smaller holes in it, you can get up to the 1420 megahertz hydrogen line and start doing a lot of other cool radio astronomy work. So in the 70s, the surface was covered with aluminum panels, and it looks pretty solid, but it's still see-through. It's like if you took an aluminum panel and took a hole puncher to it, put little holes all through it. So now you've got a much more sensitive telescope because you can control this surface a lot better than you could chicken wire. So you've increased the sensitivity, you've increased the frequency range you could look at, and do a lot more science. And this is a good picture where you can see the line feeds. So this is about a 30-meter line feed here. There's other line feeds here. And the reason you needed those line feeds is you have a spherical reflector, so you have spherical aberration. So you're no longer focusing to a point, you're instead focusing all the light to a line. So you use these line feeds to take the signals that have been focused from different parts of the dish and phase them up into a coherent received signal. So you essentially had to have a different line feed for whichever frequency you wanted to observe with the telescope. So then they said, well, we can make the telescope even better if we get rid of the spherical aberration. So to do that, they created this Gregorian dome, which you see being built here. They actually had to build it on top of the reflector, so that's the primary reflector in the background. And they built it up on the dish itself. So inside that dome, you have 2 parabolic mirrors, a secondary here and a tertiary here. That gets rid of your spherical aberration and focuses everything to a point. So then you're going to have all your receivers up on a turret inside the Gregorian dome. So these are pretty hefty mirrors. It's a 22-meter and a 9-meter reflector up in this dome. So this is what it looked like in about 1998 or so. Brand new shiny Gregorian dome. Just to give you an idea, that's essentially a 4-story building just hanging from the dome. So at this point, you're really 900 tons up there. So there's multiple levels in here. You can't really see it, but there's a hole in the bottom. Then the secondary is along this part. Tertiary is down here. And then you have essentially 3 levels of equipment, including the receivers, one of the transmitters, and waveguides, and all sorts of stuff like that. So over here in the dome, we have one radar system. This is an S-band system, 2.4 gigahertz or 12.6 centimeters. It's got 1 megawatt of output power, and it's a continuous wave radar. Now the line speed, typically they're using a P-band radar, so 430 megahertz, 70 centimeter wavelength, 2.5 megawatt peak power, and that's a pulsed radar system. So this is mainly used for atmospheric studies. This one is mainly used for other planetary astronomy beyond the atmosphere. So Arecibo is not the only planetary radar that's in use. The other one that gets a tremendous amount of use, not as much as Arecibo, but it puts in a lot of work. Goldstone is called DSS-14. It's part of the Deep Space Network. So this is actually one of the 70-meter communication dishes that's usually used to talk to spacecraft. But it also has a pretty powerful transmitter, 500 kilowatts. It's at a different wavelength, 3.5 centimeters, or X-band at 8.56 gigahertz. So it's actually really complementary to Arecibo. Arecibo, they're different wavelengths, so you're studying different regimes on the surfaces of the objects you're looking at. They're different sizes, so Arecibo is about 15 times more sensitive than Goldstone. But one of the advantages of Goldstone is it's fully steerable. It can see about 80% of the sky, while Arecibo can only see about 30%. And Arecibo can only track an object for about 2.5 hours or so, but Goldstone can track things for many more hours. So if you combine the two, you actually have a very complementary system between these two planetary radars.
Question.
Yes, sir.
Is Haystack still in that business?
Haystack does have a radar. A lot of what they do is pretty classified, so we will hear like, hey, we tried to detect something, we have data, but we can't show it to you. So, what they have, I think the current one they're playing with is a W band, so something like, I forget where that puts it, like 100 gigahertz or something like that. So it's, when they can use it for astronomy, so if something comes super close, they can get really high resolution data on it, but we never get to see it. So, yes, there are smaller radars at various other places, including Haystack, but not used a lot for planetary scale astronomy. Is there another question?
Well, and is there an update talk that's been going on about the transmitter that might be installed for radar? Do you have information on that? It's been on again, off again discussed.
Yeah, it's very much been on again, off again. It would be interesting to put something like a Ka-band sort of system. One of the problems you have is the power available in those transmitters currently is not necessarily enough to make it worthwhile. You would need some improvements in transmitter technology for a system on Green Bank to exceed the Goldstone system, and it would be difficult to ever get up to the Arecibo system. And then the other question is how do you fund it? You know, it always comes back to the money. So it's something that should be kicked around and kept in mind, but I don't think that's necessarily a near-term sort of thing.
What kind of power would be useful?
If Green Bank had a K-band at less than 100 kilowatts, it would pretty much rival Goldstone. If they could get hundreds of kilowatts, they could get more closer to what Arecibo can do.
Not in my lifetime.
No, it all depends on how the technology is improved and scaled. So just since I'm concentrating on Arecibo, just summarizing it a little bit, planetary radar has actually existed at Arecibo its entire history, since the 60s, and you'll see some mentions of that. And we like to say it's the largest, most powerful, most sensitive, most active planetary radar system in the world, because it is, and it's awesome. essentially it's a 20-acre collecting area, an antenna gain of 12 billion, which is pretty good. And the other thing is, we can use this to study solid bodies from Mercury all the way out to Saturn. And that limitation is partly just because it takes light so long to get to Saturn and back that if you try and do things even further away from Saturn, by the time the echo comes back, it's set. So you just can't track it long enough at RCO. And what I concentrate on is asteroids. So what's important to me is how well you can look at potentially hazardous asteroids, PHAs. So any PHA that comes within about 20 meter distances or 0.05 AU, we can hit it with radar and learn something about it. And even any asteroid sort of on the 10 meter scale. So Tunguska was probably a few tens of meters. The airburst in Chelyabinsk 5 or so years ago was probably about 20 meters. So something 20 meters can do some damage. And we can detect and characterize those objects if they come within sort of 0.01 AU or so. All right, so the basics. So the first thing we do here at RCO, well, not here at RCO, but there at RCO, over in this valley here, there are diesel generators. We've got 4 diesel generators that put out 2 megawatts of power. You put that on a high voltage line that goes up this catwalk that if you wish you could walk up to the platform, 500 feet in the air. And it snakes its way through into the dome there. We have not only 2 klystrons, so vacuum tube power amplifiers. You take that 2 megawatts and you can turn it roughly into about a megawatt of coherent emitted power, which I think is amazing. 50% efficiency on that power going out into space in a useful way. So we then transmit with a circular polarization. So you're going to start in this dome, you're going to transmit, you're going to bounce off the tertiary, the secondary, off the primary, go out into space, hit Eros, who's not actually that close. Then it reflects off Eros, hits the primary, hits the secondary, hits the tertiary, and right before that signal gets back, you turn off the transmitter. You turn the turret in the dome to take the transmitter to the receiver in the focus, and then you record that echo for the same amount of time. And we record that in both circular polarization polarizations, so we can find out how much the signal has been depolarized by the target. So the problem with radar is because you're going back and forth, it scales as 1 over r to the 4th. So you lose your 1 over r squared going out, you lose your 1 over r squared coming back. So your signal is dropping off to with the 4th power distance. So that means you want big objects that come close and you want to hit them with a big telescope with a lot of transmitted power. So that's why you use RCO. And the great thing about this kind of astronomy is you're controlling the signal. You know what you sent out there. So when you look at what comes back, whatever happened to your signal is due to the properties of the target you bounced it off of. And that's really the powerful thing of radar. So like I said, what do we transmit? We're controlling the signal. There's really two main modes that we run in. One we call continuous wave. That's where we're sending out an unmodulated monochromatic tone. So essentially you just send out a delta function and see what comes back to you. And then after that, we can try and do delay Doppler ranging or imaging. So in that case, instead of being unmodulated, we now phase modulate the signal that goes out. So every so many microseconds or fractions of a microsecond, we're taking the phase and either choosing to flip it or not flip it in a pseudo-random but known way. And the frequency that you're flipping or not flipping that phase is going to turn into resolution in time, or equivalently resolution in range. So at RCO, the fastest we can modulate is 20 megahertz. So we can flip-flop that phase at 20 megahertz, and that translates to 0.05 microseconds of time resolution, or equivalently 7.5 meters in range resolution. Keep in mind these things are millions of kilometers away, and we're going to get this sort of resolution in our images. And so this 20 megahertz is a limitation of the klystron transmitters. That's as fast as we can go. That's as high of a bandwidth we can put on the klystron transmitters.
Question?
Yes.
How long at a time is your pseudo-random modulation sequence?
It varies. We can choose how long that code is. It can be anywhere from usually sort of either 1,000 bauds, 1,000 flips or no flips, up to 65,000. We also have a long code system which doesn't repeat for like the equivalent of many astronomical units. So you can choose depending what your needs are for the experiment.
What was your carrier frequency again?
Arecibo is at 2.38 gigahertz, but it varies from site to site. Like Goldstone is 8.56 gigahertz instead. Is there a question?
How do you dissipate 1,000,000 watts of wasted heat?
A lot of water.
There you go, somewhere.
So yeah, I didn't mention that, but there's an enormous cooling system up there. I don't know if I have a good picture of it, but there's 6 huge radiator fans. There's 300 gallons per minute of cooling water being pumped through the dome continuously.
So that means if you're put 2 megawatts going into the thing, 1 megawatt of RF, there's 1 megawatt of heat going up there.
And then another megawatt when you turn the
And that's all right up in the dome.
It's all in the dome. Yeah, it was one of the big projects recently was replacing the heat exchangers to boost the cooling for that. Okay, so that's what we transmit. What do you receive? So the receive signal is incredibly weak. It's about 10 to the minus 27 of what you sent out. And, and we still do science with that somehow. And that's all because of the distance to the 4th power hurting you. So the signal, you get it at the receiver, then it travels by fiber optic cable from the dome all the way down to the control room. During the course of that, it's mixed down a couple times from 2.4 gigahertz, eventually down to, eventually down to baseband after enough steps.
Is it RF over fiber, or are you digitizing it for feed?
I recognize some of those words. I must admit, I am not an engineer, so Tapasi, maybe Tapasi, is ready to say anything?
RF all the way down. You do one stage, a 2-stage down conversion, but then digitized in the control room.
Okay. Yeah, I guess it comes down to the control room at I think about either 1.5 or 750 megahertz, and then it gets mixed down further. So with the continuous wave, essentially you just have you're recording voltage versus time in the 2 polarizations, and you just Fourier transform that, pick out the frequency components, and get information from it. And I'll show you examples of that. For the imaging, you have to take your signal that you received and cross-correlate that with the signal you sent out to get your range information, and then you Fourier transform that to get your frequency information. And you'll see plenty of examples of this. So I'm going to have to go in more detail for the astronomy, for the asteroid stuff, but I think at this point we can at least show some pretty pictures. So you might recognize this one. This is the moon. Kind of looks like a watermelon to me, because it's really bright and then it's got these stripes. I'm sure you guys can answer. This is your first test. So why does it look like it's light and dark striped? What are we actually seeing?
Beam width.
Yep, that's the beam pattern. So this is your main beam, these are your nulls, and then your side lobes around. So you look at this, and it looks a lot like an optical image. It looks like what you picture the moon to look like. But one of the differences you see are some of the craters are really bright, and this is actually giving you an indication of the surface roughness. So radar is not just giving you physical dimensions, sort of like an optical image, but it's also giving you an idea of how rough a surface is, because if you bounce radar off a plane mirror, you're just going to switch the polarization because it changed directions. But if you have a rough surface that lets you have multiple scattering from objects or rocks and regolith that are sort of the same scale as your radar wavelength, you can depolarize your signal. And what this is showing you is around these craters, the ejecta is a lot rougher than the surroundings. And that's one of the things that radar can pick out. So yeah, that's one image of the moon. This is like a really raw image. This is like straight off the telescope what you would see in one of these radar images. This is a blow-up of the Aristarchus region on the moon after Bruce Campbell from Smithsonian was able to work with it a little bit more. So this image, 80-meter resolution on this one. You can see very clearly different geologic features. You can see this pyroclastic flow that is much more radar dark than the rest of the Maria. You can see this crater with all the ejecta, indicating that it's much rougher than its surroundings. And you can see other features sort of cutting through the flow. And not just roughness, radar also is penetrating below the surface. It can get, hand-wavingly sort of 10 wavelengths deep. So in this case, we can see things that are buried a meter under the ground with the Arecibo S-band, and even deeper with the P-band Arecibo radar for the moon. So actually one of the things they're doing is trying to find buried geology, trying to pick out these lava flows that have been buried in other dust and regolith. They're trying to find lava tubes and other bits of geology that to our eye would look like they're covered in dust. But to the radar, you can actually see that there's geology buried under there. So that's one of the really cool things that they're doing with radar on the moon. And sort of, you can get, I've seen images of the moon with radar that are sort of the 20-meter scale. And that's the best global mapping we had until sort of the last 10 or 15 years of spacecraft. You had great images of like footprints on the moon, but you didn't have global maps sort of at below the 100-meter scale. And radar was really the one that was providing that sort of mapping until the sort of like the L-Cross, LRO sort of generation of spacecraft went up there. So speaking of LRO, we've actually been working with LRO where they had their own S-band transmitter system on their spacecraft, but it broke. The transmitter died. So they were in the market for an S-band transmitter that could send a signal to them, or to the moon, and that they could listen to. So we started working with them at Arecibo. So we do the transmitting, we pick out a place on the moon, well, they pick out a place on the moon, and we aim the transmitted signal there, and then they fly by it and record the echo from the moon. So they do these crater maps. These are different maps across parts of Mare Imbrium at about 100-meter resolution. And the idea that they're trying to test is rock and water ice should behave differently as a function of the angle between the transmitter and the receiver. So they're trying to map through these craters to see if there's water ice buried in them. And it's still sort of inconclusive. They've seen some craters that look like maybe they have a signature of water ice, other craters that don't seem to have that same signature. So it's an ongoing thing, trying to figure out if there's buried water ice on the moon. So Mercury, pretty much been 3 revolutionary discoveries about Mercury with radar. In the 60s, we didn't actually know what the rotation period of Mercury was. Everyone assumed that it was just tidally locked to its orbital period of 88 days. But it turns out that Mercury is not in a 1-to-1 spin-orbit resonance, it's actually in a 3-to-2 resonance, and that was determined by radar. And more recently, about within the last 10 or 15 years, studying the rotation state of Mercury with radar led to the discovery that it has a partially molten core. It hasn't solidified yet, and you can tell that from radar data. And another one of the neat things was these radar images from Arecibo that showed these really radar bright regions at the poles of Mercury. And these bright regions correspond to permanently shadowed craters. So this is evidence for water ice at the poles of Mercury, despite the range of temperatures that you see on Mercury and its proximity to the sun. There's regions that still remain cold enough to have water ice in them. And of course Venus. Venus has such a thick atmosphere, it's really hard to study it really in any way. But radar just goes straight through it, just goes straight through the optically thick atmosphere. So the first geologic maps of Venus were all done with radar. And so here in the brightly colored plot is radar of Venus. The color coding is related to essentially the surface roughness again. So you've got volcanic regions that are extremely rough here in the red. Maxwell Montes here at the front is extremely rough. But then you have plains through here that are much smoother than the mountainous regions. And so this is a map of Venus at about 12 kilometers resolution, where the goal was to get this sort of map this roughness. But if you want to, you can go to even higher resolution. This here is a blow up of Maxwell Montes, just blown up to about 10 times better resolution. And you can do geology here. You can see essentially the flows of lava that it came out of this volcano. So this is oh, and I think you mentioned, yeah, we figured out the rotation period of Venus, which you didn't know before because you could never see the surface of it. But with radar, we figured out the rotation period. So this is an ongoing project to keep an eye on Venus to look for signs of active volcanism and tectonism on the planet. This is another picture of Venus. I just had to include because look at this. This is incredible. This almost looks like flower petals or something. And you've got these other sort of concentric ring features. That's just really cool. And I don't want to leave out Mars. We can do Mars as well. So first, let's start on the right. This is a Viking 1 map of Elysium. Elysium Mons is over here, and there's various other volcanoes. So optically, you pick out this very different dark patch. But when you look at this same region in radar, you see this. So there's Elysium Mons again. It's kind of hard to see the same geologic points, but this part is over here. But there's a lot more detail in here. You can see that there's sort of a channel system connecting this region to what's off the screen here. That's really hard to see optically, but you can see a very clear connection between the regions. You can see the flows coming out of the volcano, which are not as obvious optically. So radar's sort of giving you an extra dimension to be able to do geology with. Okay, so now we're going to shift more to the asteroids, which I spend my time on. So previously, these images have really looked like sort of like what you'd see with your eye, but they're not exactly, but they look close enough to get away with showing them early in the presentation. So what do we measure with asteroids? So really with radar, all we're doing is measuring two things really well. We're measuring distances and velocities extremely precisely. So essentially that just means we have really good timing and we can measure frequencies and Doppler shifts really well. So when it comes to asteroids, we really want to measure the distance and their velocity as well as we can. And so I think this should be a little video of, this is asteroid Itokawa with a fake radar beam bouncing off of it. And what you want to look at is, so this one's coming towards you, this one's moving away. This one is a little bit closer, so you get the signal back sooner. And this one was further away, so you get the signal back later. So by timing when you get that echo back is telling you how far away the object is. And then the other thing to note is the frequency of the wave. So they're coming in at the same frequency. This one's moving towards you, so it gets blue shifted. This one's moving away, so it got red shifted. So that Doppler shift is telling you the velocity, the bulk velocity of the object in space. And that's super important because optical astrometry tells you the plane of sky. It tells you where it is on the sky and how fast it's moving on the plane of the sky. Radar's giving you that third dimension. It's telling you the distance on your line of sight and the speed on the line of sight. So if you can get optical and radar of an object at the same time, that completely determines the six-dimensional position and velocity state of that object. And if you have that, you've got the orbit. If you know the orbit, you know where it's going to be in the future, you know if it's going to hit Earth, you know if it's dangerous, and everything like that. So that's the real power of radar astrometry. So along those lines, these are the bullet points we like to point out. It's incredibly high fractional precision. It's 1 part in 10 million. So we're getting, I can tell you the distance to these objects to less than a kilometer when they're 10 million kilometers away. I can tell you how fast they're moving to a millimeter per second when they're moving tens of kilometers per second. And when you can put that into a solution for an orbit for an object, it collapses the uncertainties on that orbit tremendously. So if you have a newly discovered object, and you're able to get radar on it, you can collapse the uncertainties by 5 orders of magnitude. And what that does is, like I said, it allows you to predict where these objects are in the future. So usually if you hit something with radar, you will not lose it. A lot of times with optical data, you get a short arc on the sky, you can't fit a good orbit to it, you can't predict when it's going to come by Earth in the future. But if you can just ping it once with radar, usually you secure that orbit and you can predict where that object's going to be for decades, if not centuries. And as the last bullet said, that is exactly what you want for impact hazard assessment. If you're worried about possible impacts on Earth, you want radar data of that object. So it's not just getting the distance and the velocity to it, you can then resolve that. You can resolve that distance into a size and shape. You can resolve that velocity into a rotation state. So here's our friendly Itokawa again. You've got a point here that's the closest to your radar, and it's not moving along your line of sight, so it's not Doppler shifted, and it's the first thing we get back. We'll wait for it to restart again. Then you've got this end, it's going to be moving towards you. It's not as close to you as that point. It's a little bit further back, and it gets blue shifted. Then we'll let this restart one more time. Then you've got this end, which is moving away from you, so it's going to get red shifted, and that here's going to come back last because it's furthest away from you. Obviously, the rotation here is greatly exaggerated. It's not actually rotating that fast. But it gives you an idea that you're sampling the object at different distances from you, so that's how you get the shape, and you're sampling it at different velocities along your line of sight, which gives you the spin. And I've also mentioned the scattering properties, that by looking at objects in both polarizations, what you send out and the opposite sense, it tells you something about the roughness of the asteroid. So I mentioned optical astrometry. It's something to keep in mind about radar is it is not a method of discovery. I'm not going to go out and blindly do a survey for asteroids with radar because it's horribly inefficient. And the way you can see that is, here's the beam width of the Arecibo radar, and this is the typical field of view of an optical telescope. So which one do you want to do your discovery? You want to leave the discovery to the optical telescopes, which can try and find moving objects in their field of view. And once they're discovered optically, we can use that information to create an ephemeris that tells us where to point, how far away we think the object is, and how fast it's moving. So we need a prediction before we do our observations. But once we know where to point, we can do really amazing stuff. So I just wanted to point out how much observing do you actually do? Sure, if you want to go back here.
Just a question,
Okay.
do you have the ability to defocus the instrument for survey work as opposed to precision?
No. Survey work is just...
So you can look and say, did I get anything back? Oh, now let me do a raster of that particular area of skies. Because I got something back, let me see where it was.
You can't do it in that sense. If you really wanted to, if you knew, if you sort of had like an error ellipse on this plain sky, you could point here for a little bit, then say, well, maybe it was further ahead in RA and move here, or maybe it was a little lower in DEC and move here. You could do that. I've seen that done a couple times, but it's just not efficient.
Yes. Wouldn't you have to know how far away it is, know when to switch from transmitting to receiving?
Yes, that's a good point. I didn't stress that enough, is you do need to have an idea how far away it is so you know when to be switching from transmit to receive. Another thing to keep in mind is that obviously takes a physical amount of time. We usually give it about 8 seconds to switch from the transmitter to the receiver. That's both to turn the turret to change what's in the focus, and also do all the communications checks that say, is the transmitter really off before I open the shutter on the receiver? And is the shutter really closed before I turn the transmitter on? So
how do you do an operation center? The flight time there and back is shorter than
that is also, that's where greenback comes in. You get someone else to do the receiving. So if something is super close, so in the case of Arecibo, if something's within sort of like 4 lunar distances, something like that, you call up greenback and try and get Greenbank to be your receiver. Then you don't have to worry about doing the switching. And I'll have a few examples of that. There's actually another reason why you want to use Greenbank, and I'll have some examples. So I just wanted to point out sort of how much we actually apply this. This is the number of asteroids detected with Arecibo per year. So right now we're sort of hovering around sort of 60 or 80 asteroids per year that we detect with radar. This is a huge jump over the last few years. And, this is when our NASA funding went up. So as soon as you get more money, you can do more stuff. Before that, it was sort of just the biggest and brightest. And then once you get a little bit more money, because people are worried about things hitting us, you can do a lot more objects. They're not all the most exquisite data sets you've ever seen, but they have information about the orbits and the physical characteristics that are really important if you're trying to characterize what might hit us in the future. Even if you don't know anything about the object that might hit you, if you know something about the population, at least you can make some educated guesses. And so this is further broken down. The hatch marks here are potentially hazardous asteroids. The definition of that is anything bigger than about 140 meters that comes within 0.05 AU of Earth. So some other things can be smaller than that and be potentially hazardous, but that's just a specific definition. So this is really, these are the big asteroids that we've looked at, and the rest are smaller asteroids, sort of tens of meters, or they don't come close enough to Earth to be classified as potentially hazardous.
It looks like proportionally you're seeing less PHAs versus total targets. Is it because you're seeing stuff that's further out, or simply not a factor?
So most of this is pushing. They were discovered by an optical survey, and then within days we pinged it with a radar. So we also have to react really quickly to these. Yes?
How many PHAs are in your current catalog?
How many PHAs are there? I think there's something like 2,000 PHAs, and we've probably looked at 300 or 400 of them. So a substantial fraction of the PHAs have been pinged by radar. And total NEAs, there's like 20,000 known NEAs. There's probably millions, but we know of 20,000 of them. And radar has been used to look at about 4%.
Did you have eyes on the one last week?
Which one? 2019 OK made some news. We were able to get that one briefly before we had a transmitter issue. But yeah, a lot of times we can react quickly. The one thing we don't always know is what objects the media is going to decide are important. So I have some examples of that, of things that the media blew up for no reason. Yes?
How long does it take you to at least initially look at an object? I mean, is it an hour, day, week?
It all depends on how strong the signal is, of course, which we don't always know going into it. We have an idea of if an object is bright, you can get the astrometry in seconds, minutes. Sometimes you have to sit on it for tens of minutes or an hour to just get a little bump and squiggle in your spectrum. So it all varies, especially for these little asteroids that we know nothing about. Sometimes you go into it not thinking you'll actually see anything, and you just get, pow, this huge signal, just because it's bigger than you thought, or it's a little bit closer, or it's rotating slower than you expected. And then there's other ones that you just don't see when you expected to see them, because there's something about their properties that, usually it's because they spin so fast that their echo is broad and so wide that you just can't overcome the noise in the receiver. That's the main problem. These little guys tend to spin like crazy. Okay, so what does radar data of an asteroid look like? This is sort of, every detection starts with something that looks like this squiggly little plot. So this is your continuous wave experiment. This is where we essentially send out a delta function, and we want to see what happens to the signal. So the first thing that's going to happen is you're going to get a bulk Doppler shift depending how fast this thing is moving towards or away from you. You have an ephemeris that predicted how fast it should be moving, but the ephemeris isn't going to be perfect. If it was perfect, the spike you got back would be at 0. But in this case, this one wasn't at 0. This was an object 2015 XL1, which is familiar to everyone in the room. It happened to be a small asteroid discovered in late 2015, so we got on it quickly. So we sent out that delta function, and if it was a perfect world, we would get a delta function back at 0 hertz, right where we expected. But in this case, we got this little peak here at minus 330 hertz. So that tells us our ephemeris was wrong, but it tells us how much we need to correct it. So this 330 hertz corresponds to about 20 meters per second along your line of sight. So we can then take that information, put it back in the ephemeris, update the ephemeris, update the orbit, and then the next time we look at it, it'll be right there centered at 0 hertz. So on the fly, we are updating the orbit of this object and using that new orbit for the next set of measurements. Now the other thing that's happening is instead of getting a delta function back, you get something that's been broadened to sort of Gaussian-ish looking shape. And that's because of the rotation. If it wasn't rotating at all, you'd get your delta function back. But you've got some part moving towards you, some part moving away from you. So that's going to fatten up your echo a little bit. And the bandwidth here can then be used to estimate the rotation rate of the object. So immediately we can tell whether this is a fast or slow rotating object. And another thing we can pick out is if you have a strong enough signal, you can, this probably wasn't the best example, but you've got the signal in one polarization, you've got the signal in another polarization. I don't know if this isn't a good example because the signal is sort of the same level as the noise, which is not very scientific. But if this was stronger, you can clearly get a polarization ratio which relates to the surface roughness. And it's also been correlated to some types of composition. So there are certain, if you see a high polarization ratio, that's usually an E-type, Enstatite asteroid. If you see something that's sort of like a ratio of 0.5, it's usually sort of basaltic V-type asteroid. But then sort of like the S's and C's, the really common ones you really can't tell much about. But just by detecting an asteroid with radar, you've got astrometry, a rotation rate, an idea of its composition, and from there you can just get even more data.
Question?
Yes?
How does the spectral spreading, how do you get the size and the rotation rate out of just the spreading? It seems like there's like...
Smoke and mirrors. A lot of stuff. So I'm being a little facetious about determining the rotation rate. That bandwidth there is a function of the size, the rotation rate, and also the aspect angle. So if I point the pole straight at you, you've got no Doppler shift. But if it's straight up and you're looking at the equator, you're going to get a maximal Doppler shift. So you have to make an assumption, hey, let's assume it's equatorial, let's use the absolute magnitude to estimate the size to like a factor of 2, and then you can at least say, is this rotating in minutes? Is it rotating in hours? Something like that. You can at least get that level of measurement out of it. You're not going to say, this is 17.2 minutes plus or minus. You're not going to do that immediately from this data.
So your total energy and the aspect ratio will give you an estimate of size.
And this is important to compare to optical observations because optically, usually you have to figure out the period of something. You just look at the brightness variation with time. And you have to watch an entire period of rotation to figure out the period. But here we're measuring instantaneous rotation rate. So even if this rotates in 5 hours, in 1 second data, I can, oh yeah, it's rotating in something like 5 hours. So it's a good check, consistency check with the optical data. Okay, so we get past that. You've corrected your orbit, you've got your frequency dialed in right. Now you can try and do ranging. And believe it or not, this is one of my favorite radar images. It does not look like much. It is one bright pixel in a field of snow and noise. This is cropped out of a much longer code. Someone was asking about the code lengths earlier. This is, you can imagine this for it, but I've just cropped it to where the asteroid is. And the reason I like this one is, even though it's just 1 pixel, I know exactly where in space that pixel is. I can tell you within 1 kilometer where that is in space for something that's 10 million kilometers away. And in this case, for 2013 LB2, when we compared that to the ephemeris we were using, the difference was an Earth diameter. And if you're worried about things hitting Earth, you want to be able to make that sort of correction. So this could have been the difference between saying this might hit Earth and not hit Earth. And radar has that sort of power. And so I really like that image, even though it doesn't look like much. It's special to me. But now the really fun stuff happens if you can start resolving that 1 pixel into lots of pixels. So now we need to talk about a radar image of an asteroid. So I have my trusty inflatable cosmic microwave background beach ball from Karen. So we're going to take this 3-dimensional shape and we're going to have to turn it into a 2-dimensional radar image. So this is going to be our asteroid. So there's some point on the face of this asteroid that is the closest thing to you. So that is the green point on the images up there. And then around that green point, you're going to have a bullseye pattern, concentric circles of points that are all the same distance from you. You're all the radar. So you've got the green points the closest, and then there's sort of slices through the shape that are all the same distance from you. And then the green point also has no Doppler shift because it's all the rotation of this at that point is all in the plane of the sky. None of it's towards you or away from you, so it's not Doppler shifted. But as you move to either side, you're going to get Doppler shifted. So you take a step to this side, this is going to be blue shifted a little bit to you. Something over here, you take a step to this side, it's going to be red shifted from you. So you have lines across the asteroid that are the same Doppler shift. And then, essentially what you're doing is you're taking this 3-dimensional shape and you're squashing it into 2 dimensions. So you just smash it. And obviously the problem you get there is you now have your northern and southern hemispheres smashed into each other. So there's an inherent ambiguity in radar data of you don't know if you're looking at a point right here or a point right here. They're both the same distance from you because they're on the same circle, and they're same Doppler shift because they're on the same distance from the rotation axis. So that's one thing you gotta keep in mind. You're essentially smashing things down the spin axis of the object. So we're going from a sphere to an image like that on the right, where you've now, your green point, which is the closest thing to you at 0 Doppler shift, is going to be in the middle of your image, and the closest, so you're now at the top of the screen. I'm going to confuse you a lot by having you either at the top or the bottom of the screen, depending on the image I show you. So just to keep you on your toes. So right now you're at the top of the screen, so your green point's the closest thing to you. Over here on the edges, your blue point is blue shifted, but it's also, so your blue point is blue shifted, but it's also further back on the asteroid, so it's going to appear further back in the image. So your blue point maps over here, this red one on the edge maps to here, and then these blue points map to the same thing. So this point and this point map to that point. So you can't tell them apart in a single image. And the same with these dark red points, they both map to the same point. So that's what we call the north-south ambiguity. So in any certain image, there can be multiple points in the asteroid mapped to the same point in the radar image. But if you can get enough radar data at different rotation phases, different aspect angles, it's not always the same 2 points that are ambiguous with each other. You can start to break that ambiguity by having different points be ambiguous to each other. So now that you're experts in radar imagery, this is just a simulation of Itokawa again, asteroid Itokawa rotating here. So you're the transmitter, you're going into the page. This is the CW spectrum you would see, which is telling you something about the spin and the shape. You can see when you've got it broadside, you get a nice wide echo, like right now. And then as it turns to end on, you see you get nice skinny. And you can see sort of like it kind of has this two-lobe nature every once in a while that's indicating that it's this two-lobe structure. But now this is a imagine you had no noise and infinite resolution, this is what the radar image of Itokawa would look like. So just to give you an idea of how you can translate a 3D shape to a 2D radar image. But that's fake, we want real images. But first, another test. What object is this in the solar system? I hear muttering.
Saturn.
I hear Saturn. All right, this is Saturn. This is about as far out as we can go with the radar is Saturn. So there's a couple weird things about this. What's missing from this image? The planet. Saturn is missing from this image. Saturn. So yeah, this is just, you can only see the rings, and that's because Saturn's not solid. The radar signal just gets sort of refracted and attenuated, and you never get it back from the gaseous part of Saturn. But the rings are ice and dust. So you can happily get a radar echo off that solid, these solid particles. The other thing that's weird about this image is pretty subtle. So just to be confusing, like I said, you're now at the bottom of the screen going up. So you can see here, there's no echo. And why is that? Because that's where Saturn is. So Saturn's really an image. It's actually casting a radar echo across the rings, because Saturn's in the way, so you're not getting any echo off the rings back here. So Saturn would be placed sort of in there. So another weird thing. Okay, so you're coming from the bottom of the screen. You'll have to believe me, but this is the Cassini division, and you got the outer ring and the inner ring. But what's weird about the rest of the image? Can you see the Cassini division the whole way around? The rings are crossing.
Yeah, the rings are crossing.
And that's because radar is weird. And that's because this axis is speed. It's not physical dimension exactly. It's Doppler shift or speed. So you've got your outer ring, which you remember Kepler's laws. Your outer ring means it moves slower. So it's less Doppler shifted. So when you go into Doppler space, this is the outer ring. This is the inner ring because it's moving faster, so it's more Doppler shifted. And that's still the Cassini division. So in radar, it looks like they actually cross because there's a point in distance and speed space where the rings actually match each other. Even though you know physically that's not happening to your eye. In the radar it does. So you get these spots where the rings cross. So I'd like to show that because it's a good example of how it's not quite an optical image or what your eye wants to see. It takes some getting used to. So we've been talking about Itokawa a lot. So how do we compare to spacecraft? So before the Hayabusa spacecraft from JAXA went to Itokawa, there was radar images there. This is what the radar saw for the size and the shape and everything. And this is what Hayabusa saw when it got there. It's really close. So you could have said from this image that it's sort of this maybe double lobey kind of thing, and there's a sort of an angle between the two parts of the head and the body. And I always wonder, see this rock here? See that bright pixel there? I always wonder, maybe that's actually picking up that big rock on the end of Itokawa. So this is really helpful for someone planning a space mission. If they know how big something is, how it's rotating, what it looks like, what are some of the bulk properties of it. That's really important for mission planning. And the other side of that is it means radar is a really inexpensive way of studying populations of asteroids. You can't send a spacecraft to all 20,000 near-Earth asteroids, but you can do radar of them a lot cheaper and for orders of magnitude less money, for orders of magnitude more objects, and get a lot of useful information. So another example, why just do asteroids? This is comets. So this is comet 103P Hartley 2. The images are here on the left. You can see this is the comet nucleus. So again, the radar is piercing through the coma, the dust, all the stuff that's normally around the nucleus of the comet, and just going straight down to the solid part. So something that's really hard to see otherwise. Radar just picks it out. So that's what the solid part of Hartley 2 looks like. And you can see it kind of looks like a bowling pin or again, sort of this too lobey kind of thing. So that's the radar data. This was a model made that's kind of two ellipsoids stuck together, and that matches the data well. And we use the astrometry, so the distance and the velocity that we measured with the radar, to inform the deep impact mission team how to do their final burn so they can fly by this comet. And lo and behold, they fly by it and it's a bowling pin. So it was really cool to just be like, oh, I already knew it looked like a bowling pin. I didn't need to send a spacecraft. Sure, but really cool image that looks exactly like what the radar suggested. And a couple other things. So Bennu and OSIRIS-REx. So OSIRIS-REx is currently going around Bennu. That's a map of Bennu from the spacecraft. And before OSIRIS-REx ever went to Bennu, and part of the reason it was chosen to go to Bennu was the radar data. So on the left here are radar images of Bennu from I think about 2005 maybe, or 1999 or 2005. And then next to it is a synthetic image made from a shape model. So we can take these radar images, these 2D radar images, and go backwards and try and turn it into a three-dimensional shape model. So these are synthetic images, which you then match these and figure out if your model's good or not. And this was the shape that came out of it, a three-dimensional shape. And you get to Bennu, and it looks exactly like the shape model. If you took this and you smoothed it out, it would look exactly like this. That boulder is that spot there. See this little bump and sort of crater thing? That's this bump and spot here. Even some of the detail here you can see in this part. It really incredibly similar, more so than I would have really expected. And I'm really glad that it matched well because it's job security.
Question. Do any of these, on any of these missions, have enough reflectivity to show up in your system? In other words, can you see whatever the spacecraft, for lack of a better name?
No, but actually one of the things that we're starting to do more of now is try and find dead spacecraft around the moon. So, like, we've used radar to track Chandrayaan-1, the first Indian space mission to orbit the moon. That's no longer operational, but it's still around the moon, so it's a danger to future spaceflight. So we have a program to track things like that. They've used it to ping LRO, they've tracked Chandrayaan, they're trying to track a smaller satellite called Una, which was part of a Japanese mission. Una is essentially a bread box, a metal bread box. It's that sort of size, and you're trying to track that around the moon. And that's difficult around the moon. So these objects actually out in space at one of these asteroids, you're probably not going to see them. Radar has also been used to, it was used to track the SOHO spacecraft. When SOHO was launched, it had some issues, and radar was used to ping it to see what its rotation state was, to see if it was rotating out of control or not. So in some cases, but you usually have to be really close to Earth to see the spacecraft. Is there a question?
No, that was a cool job. Very cool job.
Okay, that was a cool. So that's happening now. OSIRIS-REx is currently in the final phases of choosing where it's going to touch down and take a sample of Bennu and then return it to Earth. So that's really neat. Another thing we're looking forward to is recently the mission Psyche was chosen for a discovery mission. It's going to Psyche. It's a very easy name to remember. Psyche is a main belt asteroid. It's one of the largest main belt asteroids. It's mostly made of iron nickel, or at least several tens of % of its surface are iron nickel. Metal is really good to bounce radar off of. It's really easy to see. It's otherwise really hard to do main belt asteroids because they're just so far away. You can really only get radar signatures from sort of the 100 kilometer scale asteroids out there. Psyche, though, being metallic, it's several times brighter than your standard rocky asteroid. So we were actually able to make a shape model of it. So this is a shape model of what we think Psyche looks like. One of the interesting things is it looks almost like it's got a pair of craters or something in the southern hemisphere. So it would be really neat to see when Psyche, the mission, gets to Psyche, the asteroid, if there really are craters on this metallic world, which is an interesting question. What exactly does a crater look like when you slam it into metal? Yes?
So I heard one description of Ben as a clump of gravel. Did that surface and structure composition show up at all on the radar?
So as you can see, the radar itself, when you make the model, you don't want to zoom too much, so you get a sort of an overly smoothed object. One thing we're going to go back and do is try and see how much of this roughness was really seen in the radar data, because you usually kind of assume it's speckle noise or self noise, or so you kind of smooth over it to get the bulk features. So like the bulk features are there, but it is a question how much of that could you have teased out of the radar, because they got there and they're like, holy crap, there's a lot of boulders here. So that is something you can try to back out. But yes, these asteroids, they tend to be just piles of gravel. They're asteroids that have just been blasted to smithereens and reaccumulated, blasted to smithereens and reaccumulated. So essentially they're just gravity holding the gravel from your driveway together. And this sort of shape that's kind of diamond shaped with the plump middle is exactly what you'd expect to get from a pile of gravel under its own gravity that's spinning. You would expect this sort of shape. As it spins up, it kind of moves to the equator, and you get this round shape in the middle. So this is kind of what we expected it to look like, and we were right. So a lot of the objects we look at are kind of nondescript and roundish. You may have heard of this one, Phaethon. It's one of the largest near-Earth asteroids. It's the parent body of the Geminids, if you're a meteor shower watcher. And it's of great interest, partly because it's a parent body of a meteor shower. It tends to look cometary at times. It'll go through perihelion near the sun, and you'll start seeing tails on it, like a comet. And so it's been of great interest. It's now the flyby target of JAXA's Destiny Plus mission. So it was really important that we get radar data on this object. This was the first object that we did after Hurricane Maria. So we were able to get the observatory back online in late 2017 after the hurricane, just in time to get this, which was super important. So this image is not the highest resolution thing. Each of these pixels here is 75 meters, but Phaethon is huge. It's more than 6 kilometers in diameter, so you still get a lot of pixels on there. But something interesting to point out just for scale. It looks kind of like the images of Bennu that I showed, and it's got a shape that's going to be similar to Bennu. It's going to be kind of this diamond shape again, but it's 1,000 times bigger. You fit 1,000 Bennus inside of Phaethon. And another thing that's kind of a concern is with radar, we can literally measure how big this is. We can count the pixels. This is 6 kilometers in diameter. You can then compare that to other types of observations, including infrared observations, which you can infer a size from infrared. And they were getting a size of 5 kilometers, but we get that it's bigger than 6 kilometers. So there's a pretty substantial discrepancy here that we need to understand. And if you're worried about, say Phaethon was going to hit the Earth and you needed to do something about it, the difference between a 5 kilometer object and a 6 kilometer object is humongous. That's a lot of mass, a lot of volume, a lot of impact energy you need to worry about. So that's one of the reasons radar is really important. It's kind of like that ground truth to compare to other observations. So other funky things. So this is 2011 UW158 alphabet soup. It essentially looks like a space pecan to me. And it's sort of this oblong shape, and it's kind of, we've never seen something, it's kind of like ridges, parallel ridges almost over the entire shape. Never seen anything really like it. This made the news a few years back because someone said it was full of platinum and it was worth $42 trillion or something. It's hard to really understand where they got that from, but with the radar we can tell you it's not metal, at least not dominantly metal. There's nothing about this that says it has more metal than any other asteroid. It's a perfectly normal sort of asteroid. And here, this animation, you can watch it rotating there. It's really obvious. In this case, it rotates fast enough that you can just watch it rotate and say, oh, the period is 37 minutes. That's actually, this is really rare. And that's because this thing is actually really big. It's 600 by 300 meters. It's twice the size of the Arecibo dish. And something that big should not rotate that fast without going and just ripping itself apart. So this object is a rare one that's that big, but is somehow cohesive enough or monolithic enough that it doesn't tear itself apart due to its own rotation. So there's only a handful of objects that are sort of hundreds of meters in size that rotate this fast. So this was a pretty rare one to come across. And not just because it has $42 quadrillion worth of platinum. Other cool things. Asteroids have moons. Lots of them have moons. Of asteroids bigger than about 200 meters in diameter, 1 in 6 of them has a moon around it. And a lot of people don't realize that asteroids can have moons, but, well, here's proof. Radar has discovered probably more than 50 of these systems. We've characterized something like 90% of them. Radar is incredibly efficient at finding these binary asteroids, and that's because we simply, there's one, hey, there's another one, done, it's binary. Otherwise, you have to see eclipse events and occultations and optical data or something. But radar, you just pick it out, 1, 2, binary. So we see these all the time, and one of the great things about binaries is if you can watch a moon orbit something, that means you can figure out the mass. If you can figure out the size and the shape, you figure out the volume, you figure out the density. Density is really hard to figure out unless you send like a spacecraft to fly by something and watch it get deflected. So this is a great way to study the densities. And what it tells you, these densities are really small. They're usually between about 1 and 2 grams per cubic centimeter. And that doesn't work for rocks, so you've got to have a lot of pore space. So that goes back to, you've got a pile of gravel with a lot of air, a lot of void space amongst it being held together by gravity. So these are just piles of gravel with all sorts of void space in them. So here's an example of 1994 AW1. This was actually perhaps the first serious candidate for a binary asteroid from optical measurements. You could see, you could watch the light curve as the bigger body rotated, and every once in a while you'd see it drop out because of an eclipse between the two objects. But just a few years ago, we were able to look at it with radar for the first time. You've got the larger body here, you can kind of see it rotating. It's a little, not the best radar images in the world. But then you just see here's the secondary just going around in its orbit. And on the right here, we've blown it up so you can see the secondary itself. You can actually measure the size and the shape of the secondary, of this little moon. And if you watch it really closely, you can watch it turning, and its axis is always pointed at the center of the primary. And that's because it's tidally locked, just like our moon is locked to the Earth. So you can actually track that this is a tidally locked system. That's pretty neat. And we've kind of touched on this. So you kind of get the prototypical binary. The little secondary here, get this sort of diamond-shaped asteroid that's round around the middle, and the sides are reasonably flat. And we think that's because you spin this thing so fast that material just kind of landslides off the equator, and you build that up into a moon. So why stop at one moon? We've got 2 moons. Radar is the only way we've ever found triple asteroid systems among near-Earth asteroids. This is the first one, 2001 SN263. You see 2 little dots in each of the radar images. And we've seen this a couple other times. 1994 CC, you've got a little dot down there, a little dot there, triple system. But then, just before Hurricane Maria, we got this guy. This is Florence. We've got the primary asteroid here. Then we've got 2 moons going in orbit around it. And this is some of the better images we've ever gotten. If you can see on Florence, there's just a wealth of information here. Just look at the shape of the leading edge and how different it is depending on how what position it's in its rotation. It's kind of hard to see, but you can see like multiple ridge lines on that edge. Here it's a little hard to see, but there's like a clump of things that look like craters. So you're doing geology essentially on an asteroid with the radar. And then here's a on animation, you can see the two satellites moving. It's a little weird because, again, this is not what your eye would see, because this dimension is speed. So the satellites seem to cross the primary, and that's just because the asteroids are orbiting slower than the primary is rotating. So the primary is big this way because it's physically large. It's wide this way because it rotates fast. And these little satellites are always sort of within that echo width because they're orbiting slower than the primary rotates, which is always a little weird to think about. So you've got this big asteroid, little tiny satellites that are only a couple hundred meters. You would never detect this by any other means. Only radar would pick out these asteroids. And in fact, the inner one has probably the shortest period we've ever seen, about 8 hours for it to whip around the primary. And we get weird looking things, like we call these contact binaries. They're essentially peanut shapes, where you've got essentially two objects about the same size that are smushed together and just rotating together like a peanut. And we see these, again, about 1 in 6 asteroids that we look at, sort of these double lobe things. So most likely these try to become a binary and fail, just kind of heaped back together. And then we get other weird things. This is the rubber ducky. This is an asteroid called 2014 JO25. We've got some really amazing images of it. And it looks like it's got one lobe here that's kind of the head and one lobe that's kind of the body. And it looks a lot like the comet that Rosetta went to. It almost looks exactly like it, except it's factor of a few smaller. Then we have things that looked like they were contact binaries. This is an object 2017 YD5. The first images we got of it kind of looked like a head and a body, but we looked at it a little bit later with Arecibo and Green Bank, and this is what we saw. It's actually 2 bodies the same size going in orbit around each other. So this is like a contact binary, but they're actually in orbit about each other. And these are pretty rare. These are just like triples. Triples we know of 3. We only know of 4 systems like this, where you've got 2 objects orbiting each other that are about the same size. So that was a really neat find last year. And another reason that we sometimes use Green Bank is not just if something's too close for Arecibo to switch back and forth, or Goldstone to switch back and forth. It's if something, if it's too close or if it rotates really slowly, you don't get much of a bandwidth to the echo, which means your image comes out really narrow. So in this case, this was a slowly rotating object that came really close, and that frequency resolution that we can get depends on how far away the object is. Say you get 10 seconds of data, you can get roughly 1/10 of a hertz resolution. But what if the bandwidth of your thing is less than 1/10 of a hertz? You don't get anything in your image. And that's what happened for this object. When Arecibo looked at it by itself, that was the best image we could get. It was just all smushed into one column there. So we had Goldstone transmit to Arecibo, and once you do that, you just receive for as long as you want. So you integrate as long as you want, you can take whatever FFT you want, you get whatever frequency resolution you want, and that thing plumps up into this. And I always try this. I think it looks like a penguin or something trying to fly. Put a little leaf on it. It's a wing. It's a little feet. That's probably the best reaction I've gotten from the crowd. But yeah, if we only had Arecibo, we never would have known what funky shape this asteroid had. It's because we had 2 giant radio telescopes that could work together that we were able to get this sort of data out of observation. And just another example of something we did between Goldstone and Green Bank. This was an object called 2003 ST220. It rotates once every 2 weeks. Incredibly slow rotation. Look at this frequency resolution, 0.0007 hertz per pixel. That's what you had to do to get any kind of detail on the asteroid. And you get that we call it the patata asteroid. It looks like a sweet potato, essentially. But it's kind of lumpy. It's got these ridges. It's got these bright spots or boulders. There's other spots that kind of look like they might be craters. So again, you're essentially doing geology on another body from the ground. Okay, so I think this is I've probably gone so far over time that we should start wrapping it up. So hopefully I've kind of convinced you that radar is a pretty unique method of studying anything solid we can get our hands on, pretty much. It's probably the most powerful method of post-discovery characterization of small bodies. You can do so much if you can get radar images of an asteroid. I told you about the fractional precision. That's really invaluable to impact threat assessment, which is a very important thing these days at sort of the government, federal level. Radar adds dimensions of surface roughness and being able to penetrate beneath the surface to reveal things that you can't see with your eye, which is incredibly important. And I also pointed out that really the resolution that we're mapping objects with cannot be surpassed except by sending $100 million, $1 billion sort of spacecraft to an object. So for, we get a couple $1 million a year to do this, and we can return sort of spacecraft flyby level science for a few $1 million a year for dozens of objects, which is incredibly efficient, so we should get more money.
You'll need more.
What the line feeds punctured the dish surface in the hurricane?
Hey, what's my next slide? It's hurricane stuff. So we can really quickly look at some hurricane stuff. This is just a graph of rain, let's see, it's velocities, air pressures, and rainfall. So Hurricane Maria hit the island in September of 2017. I was there, I lived through it. Probably part of the reason I moved. But it got up to, the gusts were up to about 110 miles per hour. We went straight through the eye, which was an interesting experience, going outside and being like, oh, it seems like it's over, and then everything happens again, but I felt the wind going in reverse. Oh yeah, it was like 2 feet of rain in 5 hours. It was crazy. So this is what the telescope looked like after Hurricane Irma came through a couple weeks before, and then after, you can see the line feed disappeared. In the middle of the storm, it just snapped and fell through the dish. And it's kind of hard to see, but between these two pictures, you can tell that the dome was pressure washed. So here's what you were looking for. In the top left there, you can see chunks of the line feed. So the line feed had a bunch of these little rings on it that used to phase up the different parts of the reflection. And this is part of the outer structure of the line feed. So chunks of it just went straight through the dish and punctured the panels. Here's more spots where chunks of it wasn't just the line feed. Also, I don't know if I might have taken the image out, but the catwalk that goes from the visitor center up to the platform, the floor out of that was pulled out. So giant chunks of steel just went straight through the dish. So there, a lot of the panels were damaged, but it was sort of on the scale of 100 or so panels out of 38,000, so in the grand scheme, it really wasn't that bad.
They repair them?
Sorry?
They repair them?
They certainly were working on it.
It's not really going to repeat the sensitivity of the dish.
Right. The bigger problem is the dish is now actually warped. So actually at the S-band radar frequency, the gain is down 30% because it's been warped by the hurricane and some motion of the ground soil has actually caused some sensitivity issues there. This picture, so this is underneath the dish, so the dish is above this. This is the water pump. Unfortunately, that's the exhaust, not the air intake. So the air intake was underwater. There's about 10 feet of water here. We have a helipad. I don't know if it's allowed to be called a helipad, but you can land a helicopter on it. We had helicopters coming in with food drops and things like that. This is the head operator working a ham radio. Sorry, this picture. because no one knew we were alive. We were cut off. He's the reason my parents knew that I lived through a hurricane. It's because he got on a ham radio and had called a ham in Virginia who called my parents' house and told them I was alive. So that's really, so hams are good people.
Is he Angel Vasquez?
That's Angel Vasquez.
Oh my goodness.
Yeah, he's a cool guy.
This is just some other pictures of stuff like, they actually they brought a kayak up so they could go and service things and see how things were damaged. That's just a recent picture. This is a Puerto Rico will rise up. Yes. Serious things.
I have two questions, but I'll blend them in the single one. So we are a group of amateur radio astronomers. Some of us are amateur radio operators. And we don't have a receiver class antennas or megawatt of power to transmit. We just can bounce a signal to the moon, and that's all. Do you have any sort of scientific recommendation for amateur radio or radio astronomers when they can do something about radar observations, like bouncing a signal on the moon and measuring the Doppler shift of that signal or stuff like that? That's part one. And the second part is, do you advertise when a receiver is transmitting so that public or amateur astronomers can have a look at that signal? If they have good dishes, let's say, we have access to the 20-meter dish antenna that is here, and we can point it to that object at that time. So we have a dual observation of that. Of course, with a very lower resolution, you know, but we can measure something. Can we help?
We want to see some link budgets. We want to see some link budgets.
So, could you see something? Maybe it just needs such a large collection area to get much of it.
Yeah, I'm not talking about those small asteroids, but maybe something bigger than small things.
So, there have been a few professionals who have used, who have piggybacked on radar observations and been able to see something when an asteroid comes super close and is incredibly bright. So you might be able to see something. I don't know. You might be able to get sort of some kind of blip. The problem, part of the problem is we are correcting for the motion of the object, so the Doppler shifting of its motion in the sky for our telescopes. So you would have to find it, but it would be drifting. You'd be drifting through frequency. I don't actually know what scale, but you'd have to worry about trying to find a signal that's drifting through different frequencies.
Integration would be an issue.
I think so.
Is the moon painted frequently?
I'm sorry?
Is the moon observed frequently? Because that would certainly be a signal we would detect.
I guess I wouldn't say frequently, but several times per year. Yeah, I have to think about it.
Yeah, but the observing plans are not public, right?
The Arecibo observing schedule is publicly available on the Arecibo website. There's just like Greenback's schedule is available. It marks on there which are the S-band radar programs.
Patrick, you gonna get the drinking hours tonight?
Sure.
Yeah. Can we take some of this offline?
I've already taken like 2 hours.
Thank you.
Yeah, I have a suggestion for amateur radio experiments. You can run 1,500 watts maximum, and with a, let's say, a 20 or 30 meter parabolic antenna, for experimentation,
That would be the
narrow beam, so you can You can track the movement just from range.
Next, I've got Drew Wilkerson. He's from Warwick College in Pennsylvania. And he's got, instead of him doing most of the work, he subcontracted to some students, and they're going to show and tell.
We're building radio well, let me tell you first, I'm Steve Wilkerson, or everybody knows me as Drew. Okay. York College is a small liberal arts college that happens to have an engineering and computer science program. Okay, the engineering and computer science program is very healthy at York College. It's been growing about 15% for 20 years, so it's doing really well. We were asked to build a radio telescope, okay, as a community project-based initiative. We usually do capstones. Our capstone design has to have a design and build something, okay? And in the past, it's always been formula cars, Baja cars, and competition type events. More recently, the students have shown an initiative that they want to do things that are community-based, where we're putting something back into the community. And that's how this came about through one of our professors and Kerry Smith at the Astronomical Society. He'll tell you that story for sure. So this is the telescope that was out there, okay, and it's going to be replaced by this telescope right here. And the students are going to tell you about this, but I can tell you for sure that we collectively did not have one Jansky of knowledge about radio astronomy prior to this project, okay, if you know what a Jansky is. So with nothing, no more, you guys come on up and we'll get them started. This is AJ Berardi, Billy Ampman, and Dan Shook, okay? And they are about to graduate in 1 week. That's a good one.
Look at that foot rester. So yeah, that's actually the pipe that the radio telescope is going to sit on. So you see how big it is. Crazy. Next slide, please. So design process. So we're going to talk a little bit about the design process first before we get into the details of how it's going to be assembled. So initially we had 32 design ideas. That's because we had a team of 8 engineering students. That was 3 mechanical, so the 3 of us up here, 3 computer engineers, and 2 electrical. So everyone kind of came from a different background, and we all had different ideas, and all contributed very interesting designs. But from there, we all decided one of our designs that would be tangible. So we had 8, and then we narrowed it down to 2 as a group, 2 good designs. And then from there, we went through the pros and cons of each of those 2 to get one final design. So before we did any of that, we had to decide whether or not we were going to do polar or azimuth. So we have some pros and cons for our specific application. So polar was easier to code. So the electrical and computer guys go, yeah, polar. Like, let's not go into that just yet. We've got to look at everything. It cannot track the sun well, and Kerry wants to stare at it. He wouldn't, sit out there like that if it didn't burn his retinas. But it was a little difficult to design mechanically. Whereas azimuth was easier to build, you could track polar objects and other objects, but we needed an additional motor, but that really wasn't an issue to us. And most of the research that we've done, we found that radio telescopes around our size were as old. So, next slide, please. So design requirements. So we sat down with our customer, Kerry, and the rest of YCAS, and we came up with some specifications. Elevation would have to move about half an RPM. Azimuth would be 2 to 3 RPMs. And those are our acceleration times. So we had kind of like a baseline, what we had to meet, and then a stretch goal. So those are our accelerations for that. And then we had 3 levels of redundancy for our motor stops. So in software, we have proximity sensors. So the telescope saying elevation, it's coming down, it's going to go towards a sensor, it's going to, all right, stop. And then if it goes past that for some reason, there's a bug or something, there's a limit switch. And that'll stop it with electrical. It'll cut power. But say it's going really fast, because Kerry's like, oh, I need to look at that now. And it goes past
the limit switch still cuts the power, it's still got inertia, it's going down. We have a bump stop, mechanical stop it. Then it's tracks and it won't hit the ground, damage the dish, or hit anybody at the park, God forbid. Next slide, please. So this is one of our 2 designs that we narrowed it down to. It's called BELLA. It stands for Ball Screw Elevation Linear Actuator. So this was taking the existing structure that was donated to us. It was designed by SSE. So the original way that it worked was there was a manual jack screw to change elevation. So you have to crank it, and then in azimuth, it was held on it was some type of friction device. It wasn't a bearing, it was like metal contact. And that friction is what held it in place. So you would disengage that lock, and then you'd have to move it by hand. So we decided we could motorize the jack screw, put a linear actuator in that, and have it move up and down, and then drive a shaft through the center, put it on a bearing, spin it that way. And next slide. And this was the other design, fire, for inertia, rotation, and elevation. So this was a counterbalance design. So we would reduce our torque needed. So the way that it works, we have an elevation shaft in the center, and the whole thing kind of rides on that. And it would be motorized. Just right in there, we apply it this way or that way to change elevation. And then of course we would have a shaft driving azimuth like that. Next slide. So, and this is the first iteration of our final design. So we took BELLA and put it on fire, and from the ashes, it was a phoenix. I can't take credit for that. That was Bill that came up with that. He drew up a little cartoon and everything. But, so we combined the 2. We would have it counterbalanced, and we would have it driven by a linear actuator, because that seemed to be the way to go. And this is kind of like a crude design. We were trying to get the way that would piece together, get our minds thinking about it. We really wanted to work further with it. We didn't have specific dimensions for the SSE parts. So we were using kind of everything up from there, from SSE. That's the hub, and then that's the dish. We're actually missing some pieces on this. That's how crude it was. We're just, all right, here's the dish, here's the hub. That's the basics of what it is.
You probably had it on the previous slide, but what was the spec for the range of azimuth?
The range of azimuth? I didn't have it on there. I think it was
0 to 100 degrees.
I'm
sorry,
360.
But 3.8.
It's like -2 to 362 for azimuth?
I'm sorry, I'm thinking elevation. Yeah, 370.
370 degrees of azimuth rotation.
Right.
Yeah, next slide. So this was our second iteration. You can see it's starting to look more like a radio telescope. We were in contact with SSE, and we got 2D drawings from them, original drawings of the dish, and then we model all that. So we have ribs, struts, all that is connecting the panels of the dish to the hub. See better here. Then on the back of the hub, we have a hub plate, and welded to that plate will be our shaft that we're rotating on. This is actually the design that we took here to Green Bank last summer, and we spoke to some of the engineers here and said, how does this look? Do you think it's tangible? What do you think? And they came back with some feedback for us. They said mainly these counterbalance arms, that would be a problem, because you're going to have vibration with that, and we don't want it to reach a natural frequency and the whole thing to break. But really, with that, when it's moving, they didn't want it to oscillate as it's trying to stand still. All of our readings will be off carrying the set. We don't want that. Next slide, please. Now it's really starting to look like a radio telescope. This is the third iteration, still Phoenix. So in this one, we had truss designs in our counterbalance, so that would eliminate some of the vibrations. The trusses were bolted together, and then from there, we had members coming off the hub that we plan to weld to the hub, and we would bolt straight into that. And again, we have the hub plate and the shaft welded to it. Everything kind of looks more professional, more streamlined. And we even added holes at the bottom of the hub plate for water to drain, because we didn't want it to fill up with water, and then that would increase the load, and maybe the bearings of the shaft wouldn't function properly. And not yet. So since we had everything modeled, we had
the full weight, load, and we had our torque requirements. And from there, we were able to size our linear actuator. And the linear actuator that we found we needed was too much money. So we decided to switch to a motor driving the shaft directly there. You have a question there?
How much is expensive?
Expensive.
What does that mean? Give me a dollar number.
So we were on our budget.
Yeah, it was like $10,000.
And at that time, our budget was only $10,000. We got some donations, and it got bumped up. But at that point, we were over budget. We were like, this is an engineering problem now, so we have to solve it.
The linear actuators we use are under $100. They're stolen from another industry.
Well, this thing weighs about a ton, and the stroke we needed was
About 30 inches.
pretty decent.
Yeah, that's the problem with the stroke.
Yeah.
Yeah. Next slide, please. So this, fourth iteration, Phoenix Mark IV. This is the final design, moving in azimuth and elevation. You can see we have a couple changes here, but I'm not going to talk about that. I'll have my team member here, Dan Shook, talk about that. Dan? Next slide.
All right, I'm going to obviously discuss the final design that we came up with.
Dan, move into the screen view.
Stand in the red zone if you're on.
Is this okay standing over here?
Yep. Yeah.
Okay. All right, so this is just to give you an overall perspective of the size that we're talking about of the radio telescope. So we put a 6'2" man standing next to it, and you can see
You
that.
have to be 6'2".
Well, that's about my height, so now you can visualize it's about 2 to 3 times me stacked on my shoulders. And the dish itself weighs about 1,200 pounds because it's an all steel, stamped steel dish. And the whole weight of the whole assembly will be about 2 tons once it's complete. And then the diameter of the dish, you can see, is about 15 feet or 4.5 meters. And the counterbalances alone weigh about 1,200 pounds, just to give you an idea. And I want to give a special shout out to a fellow named Cliff Bates. He did a similar radio telescope project about the same size, and he documented it very well. And that gave us a lot of information on how to proceed with our design going forward. Do you have a question? Next slide, please. So talk about some of the big issues that we ran into with our design. Obviously, the fact that it's such a large project, we're a smaller school, some of the parts we would have to get made outside of it, because we don't have the capacity. We have a really nice machine shop, but it's only so big we can fit on the machining centers. So that was one thing. Now you're talking about, this whole assembly weighs several tons, so you have to think when you're going to install it in the part, how are you going to do that? You have to think of how you're going to rig this thing up once everything's complete. So another issue we faced. And then, as AJ kind of alluded to with our parts, the larger parts are going to cost a lot more money. And with limited budgeting, we had to think of that the whole time. How can we make this as inexpensive as possible, but also make it the best thing that we can make it. Another thing with a big dish like this, you're going to have significant live loads such as wind, rain, snow, ice. A little diagram here shows you the static loading of about 2 tons for the whole structure. And then we have about 3 tons at a 90 mile per hour wind. So obviously, most likely it's not going to see those kind of loadings, but when you're designing something, you always have to design for the worst possible thing because you don't want it to fail in anything it would ever see in its life on Earth. And then, to move several tons of metal, you have to think, you got to put decent sized bearings, motors, all that kind of stuff. So you have to put a lot of consideration into how this thing's going to pivot on its different axes to make sure that it won't fail and it will be able to pivot smoothly and accurately to be able to position at the sky to receive signals. Another thing, sustainability. This will be outdoors, so you're going to get rain, snow, melting snow, wind, debris. This thing has to be sealed to the outdoors. It has to be able to withstand water getting into the inner electrical components. You also want to make sure that you can replace anything that might need to be replaced. So you want to make sure you don't put this thing together, and if somebody wanted to ever replace a little electrical component, they'd have to move the whole satellite, take it all apart just to do that. And then you also have to think that lubrication, you're going to have pivot points, so you want to make sure that it's really easy to lubricate, because if it's not easy, nobody's ever going to do it, right? And then this represents our college, so we want to make sure that it's a really professional design, it lasts a long time. It also represents YCAS in the local York area and all the businesses involved, so it will be something that everybody can be proud of. And next slide, please. So this is an overview of the main components. The main thing to notice is it's very modular, so what we try to do, because it's like a big structure, is to make it into smaller, somewhat pieces, so that it would be easier to make at the school and local businesses that are helping us. The existing dish that was donated to us, so that was given, that was basically all we had to start with, is the dish. So everything else was left to the imagination, created out of thin air, and with the help of research. And the dish right now is disassembled, so to get it up and running, once we get the structure built, will have to be put together and refinished, because it was sitting outside for a while. So there is some work involved in that, but it's a nice starting point when you have something to start from. That will connect to what we call the triangle connector. So that is the connection point to the dish, to the rest of the structure. And you'll notice that that also has the counterbalance weights, which will consist of basically barbell plates that we can, as we're assembling it, put it on to get it perfectly counterbalanced and put more on or less as needed. And that will all pivot for the elevation movement, what we call the elevation frame. And within that frame is a gearbox, which will have a stepper motor, and that will provide the elevation movement. And I'll go into each piece in more detail. And then that will connect to the azimuth, which will turn it in the azimuth direction. And then finally, the post is actually 14 inches in diameter. You saw it in that picture. AJ just showed you, and it weighs, the post alone weighs about 600 pounds. Pretty big post. Go ahead, next page. So connecting to the existing dish. So we went over that. We have the existing dish, and we have the triangle connector. So one thing that was a benefit of this over the last previous design is we're not doing any welding to the existing dish. One worry there was that when you weld to something, it's going to distort it. So we want to avoid that. So what we did was we basically took what was given and we figured out a way to connect to it. And then you can see that it's all made of structural steel and weldment basically, so we can cut up smaller pieces, weld it together, and we have our connection point. And it will also incorporate eventually a stowed position lock, which will allow us to lock it in position in the event of like bad weather or something, to keep the dish in a safe position. And up here on the left, you can kind of see the evolution of how, like I said, this was created out of thin air. So, in the beginning, it just started out as like this basic tubular frame device, and it evolved into what you see as our current design. So this is the elevation frame, so the triangle connector and the dish connect to that. And within the elevation frame, you have the elevation gearbox, and that is a 50-to-1 gear reduction. And you can see the shaft runs through it. And the shaft is supported on each end by 2 Timken spherical roller bearings, which will allow slight shaft misalignment for manufacturing tolerances and stuff. And they're greasable, so maintenance goes into the whole thing. And you'll notice that the slots in the frame itself allow everything to basically be disassembled easily. So if something for some chance would ever have to be replaced, it's pretty easy to do that. And the whole thing is connected by means of compression sleeves. That's the fender drive labeled in the diagram right there. And they basically slide on the shaft and slide into a bore, and then you tighten screws on them, and they expand around each part. And they have significant holding torque. And then you won't have keyways cut into your shaft, so you'll strengthen the whole design by using those. And they're also, you can take them off pretty easily. All right, so once that's done, connects to the azimuth. And the azimuth is kind of like the brains of the whole thing. There's a lot of work that went into that because a lot of stuff was involved in just this part. So the main component is the slewing ring, which they use in bucket trucks and excavators to rotate on. And the nice thing, it's kind of like a giant bearing, but on the inner race, you can get them with gear teeth. So it not only gives you a way to rotate the whole thing, but it also gives you a driving mechanism because now you have a gear. So that is driven by a right angle gearbox, which is a 100-to-1 gear ratio. So the nice thing is we can use the same stepper motor for the azimuth and elevation movements, which goes into the maintainability because now if you need to replace something, you can use the same exact component on either one. And also within this, you'll see that we have an encoder, a ring encoder, which will give us really accurate position feedback, so we'll always know where we're at. And then I'll go into this a little more on the next slide. Also within this is stops. So we had, like AJ was talking about redundancy, we had limit switches to cut electrical power and a hard bump stop. And the hard thing about that switch is how do you design a switch that allows 0 to 360 degrees of travel. And I'll show you that in the next slide. So this is kind of a blown up view if you're looking down on the azimuth. And if you look at the right, around the outside there are 3 proximity sensors, each at 60 degrees. What these do is they give you kind of a check. So, you know, if the encoder is giving you feedback, you have that kind of proximity sensor feedback to make sure that you're in the right position. And it also tells you by going over 2 proximity sensors, you know what direction you're turning in. So you can always check your software to make sure that you're going where it says it's going. And then right there on the right is kind of the, it's an incorporated hard stop and limit switch built into one. If you want to play that video on. So as this thing rotates, this bar right here actually extends down into the cavity. You can't really see it in this picture, but you can see that it contacts that pivot bar. And on the end of the pivot bar is a cam action, and it will trip those limit switches at -2 degrees and all the way over to 362 degrees. And the nice thing about that is once it trips electrical power, it provides another 2 degrees of travel before it actually contacts a hard physical stop. So it gives you a little bit of time once it cuts electrical power to allow it to drift into that position. So that was one of the challenging things about the azimuth design is, you know, coming up with a way to spin 360 degrees, well, a little over and under, and also allow limit switches to be incorporated in it and a hard stop. Then finally, working down the design, we have the post, which connects to the foundation. And luckily, we contacted our civil engineering professor, and he set us up with 2 local York companies who provided enormous help on this because we're mechanical, we design the steel and all that, but to connect to the ground is a whole other science in itself. That's something that we didn't want to tackle too much because we had so many other things to do. So what we did was we devised wind loadings, you know, all those live loads I talked about, and once we came up with all those, we had something to give to them to say, we need a foundation to withstand these loadings. And so GTA, they were kind of a geotechnical part of the engineering. What they did was they went to the site, pro bono, drilled down into the soil, and they determined what the makeup was. And what this does is it gives you a bearing capacity for the soil. They can pass this on to Kearney Engineering, who actually designs the foundation based on their information on the soil and also based on the loading. So now we have our foundation fully designed, and Billy's going to go into kind of where we're at and talk about the progress made so far on this huge project. Yes.
How much concrete is in that foundation?
I don't know off the top of my head. Do you?
No, I don't know either, but that'll be put in soon. They're getting ready to.
It's many cement trucks full.
Yes.
It's a 6
Yeah.
by 6.
Yeah, it's a foot deep. Probably a cement truck full.
6 by 6 foot.
And I think they have to use special concrete in some place, or you know, it has to have wire mesh in it and all kinds of things. But it was all designed by a civil engineer, that had a professional engineer, years license. So.
It was a 10-foot square base with a pillar in the center, all rebar.
Yeah.
It's pretty.
Sounds awfully familiar.
All right, so, yeah, I'm gonna talk about the progress we actually made with it, then starting back from the ground up. This is the post we have. It was donated by Lally Pipe and Tube in Ohio. We actually have Boyd Hydro and Wolf Tooling machining it right now. And the machining work and welding has been done on it. It just has to be sandblasted and sent out to be painted. And the current capstone team is working on that.
Just, what was the price of shipping this?
The price was about $400.
So we're hemorrhaging money as we're doing this,
Yeah.
just to get a free pipe, $400 to get it there.
And that took 2
This is the
weeks.
pipe, is that the pipe you were standing on in the
Yes.
first slide?
Yeah.
That's it.
All right.
Sorry.
So this is the azimuth base plate and gearbox. So everything, the dish, the gearboxes, the motors, the elevation frame, counterbalances sits on top of that plate. And so you don't want to disassemble it to fix out a limit switch or something. So there's access ports that were put in. And then the motor and gearbox have been integrated into the actual slew ring. And this, it's sitting on a mock flange, so it's not the final components. We were able to modularly test it as we went along. So this is our test cart that lets us test each component as we complete it. Then there's the backflash adjustment. So this is, in the middle is the actual flange that provides a flat surface for the bearing to sit in, so there's no distortion, it doesn't ruin the lifespan of the bearing. And then the sensor plate is in the center with the hard stop, as you can see. And then the gears mesh perfectly, give us the desired motion. It goes full 362 each direction. Slide. And then this is a close-up view of the actual hard stop mechanism. So the previous picture, it's labeled A is the plate and bearing. B is the actual hard stop mechanism, or the pin that goes in. C is the bumpers. D, the bumper contact. And then you can see how it touches the limit switches as it goes past, so it doesn't actually, it has the software stop for the hard stop. Then X is just the pivot point for that lever action.
Somebody's sneakers on.
Hmm.
Somebody's
Yeah.
feet is underneath.
Oh. That's Dan's sneakers.
No, they're not.
So, working through the project, we ran into time being a big issue. There's semester breaks where we're not on campus, and semester's only 14 weeks, but it's really only like 13 weeks. So we knew we wouldn't finish the whole thing before the end of the semester, but we wanted to be able to demonstrate both systems, the full drive system working together, the as-L. So our solution to doing it right, so we don't machine the elevation frame right there first and then weld it and distort it so nothing is, or everything's misaligned. We built a wooden prototype elevation frame that's a 1-to-1 scale that sits on top of the base plate. And then go to the next slide. This allowed us to actually mount the elevation gearbox on top of it and put the shaft through, mount the bearings. So that showed, and then we could test it together, and they both work as one system to move in a as-L coordinate system that's fully integrated. And then on the next slide, okay, so first is the electrical test bed. No, that's fine. The electrical test bed, that provides two 48-volt direct current power supplies for the stepper motors, and then one 24-volt direct current for the control system, which the control system consists of two safety relays, the PLC controller, Ethernet switch, and the motor control unit that controls the entire system. This will be mounted onto the actual base of the telescope. So this is kind of where we ended off. We had Carrie donate 3-foot dish, and we put it on some mock counterbalance arms so we could actually see dish movement. So it's a small scale test, I think about fourth the actual size, around that. And then eventually we could put a receiver in this, test data acquisition and the database integration of the whole system to test out the control software. But then we're going to work on getting the current capstone team is going to work on getting the triangle assembly together so that they can actually put full 2,200 pounds on and do a full stress test. I don't know if it'll be on that test cart because there might be some clearance issues, but on a test cart version before we actually put it together in the park.
And just to give you an idea of the cost, the metal, we just ordered the metal for this. This was $1,000 in metal. I mean, then we have to get professional welders to weld this.
Yeah.
And then we have to have it machined. So there are some costs in this. Sorry.
And then on the next slide, this is, if you want to play, this is a video of the first time that it's actually being driven by the control software. So that's one of the computer engineers, and then another computer engineer in the back, or in the front row. And then Travis reaches for the e-stop, just in case, but we didn't need to use it. This was, actually, you can see they're wearing the shirts we're wearing now, because this was about 15 minutes before our final presentation that we got to work the first time. So we were pretty proud of this moment, because it was the full drive system working as one unit controlled by the control software. They put in an as-L coordinate and it went to that position. It knew where it was. The only thing missing was the receiver.
So you got a passing grade?
Yeah, we did. With honors. Otherwise, we'd still be up there working on it. Yeah. You go to the next slide. And then one of the other things that the computer engineers and computer scientists worked on, so it was 3 computer engineers, but then about 14 computer scientists as well, working on the website and everything. They made a VR simulation of the actual observatory. So all the way on the right is the current YCAS observatory, where they have the optical telescopes. And then the blue building in the middle, that's the control room for the satellite dish. And then that's the actual radio telescope right there.
I think our telescope actually sits a little higher than this, doesn't it?
Yeah, I think the scaling was a little bit off in this image. Yeah. But yeah, it'll be.
So it's sitting higher, it's above that.
Yeah. Yeah.
The perimeters.
And this is just another view of the telescope. That one you can see it's a little higher up on the left, more detailed view of the actual VR telescope. So if you go in the VR goggles, you can actually, that's what you'll see on the left side. And then we're also going to have AR goggles, which allows you to visualize it in the room or wherever you are and go through the components, and eventually you can simulate the data acquisition and see what was actually collected through a visualization software. First we got to get it to run. Next slide. So this is a top-down view. The black squares broken into quadrants, that's just a point where someone can stand in VR, like a point of interest. It's not going to be there. But on the right is the actual observatory, and on the left is the dish. And if you click ahead, it's superimposed on Google Maps image, showing you actually like where in physical space on the Earth this will be, and more or less about the size. I think it's a little bit bigger, the telescope, but you can see where it'll be. There's a nice open field where you can actually observe the night sky and the day sky, since it's radio telescopes. Next slide. So yeah, this is going to be an access point for radio astronomy in York, PA. It can provide educational outreach, research opportunities for schools and universities, as well as amateur radio astronomers that want to assign some data acquisition, some observation that they know about. And it'll broaden the cosmic perspective in York, PA, which there was a 12-foot dish, but it didn't work, and now this one will replace it. And if nothing else, maybe we'll get free satellite TV from it. That's our presentation.
Did you do anything with the ground in order to enhance or control the interaction antenna with the ground?
On the foundation?
The ground around the antenna, so that...
No, I'm trying to, that's
We didn't, no, we didn't do anything. We just designed, or had the foundation designed.
That might be a Carrie question.
Yeah, I don't think there was anything.
I couldn't hear it. Something about the ground around the dish?
You mean like for seismic activity or anything?
No, I think he was talking about reflectivity and so there's actually a flux at the ground that people worry about, right?
Okay.
Yeah.
Well, you're not planning to transfer, is that correct?
Not that
Carrie, that's a Carrie
Well,
question.
if you're talking about the conductivity of the ground, then that has not really been investigated. I mean, it's just ordinary soil. I mean, it's
A lot of rocks.
Yeah, I know.
no, it's
The foundation is gonna be covered with gravel, right?
No, it's not, conductivity is not relevant.
yeah.
Is it undisturbed ground, in other words, original?
It's been there for decades.
Foundation?
Eons.
So
It's been there for
fill.
decades.
You're not building on fill of any kind?
No.
No.
Yeah, that's important.
Do you have a map of the environment for electromagnetic radiation emissions for human exposure near the telescope?
We're not transmitting, but it's a good question. Yes, we did a spectral survey of the area. It is polluted around the
But
public
it'd be
surface.
wise to get meters and to create a map of the different positions, you know, what the electromagnetic radiation. I'm harmed by electromagnetic
They're not
radiation. I
transmitting.
can detect it as real.
They're not transmitting.
If we were emitting electromagnetic energy, I would understand your concern, but I'm not sure I totally.
So this telescope is not
Is
emitting,
receive,
it's only
receive,
receiving.
yeah.
Still be wise to measure the environment, because even though it's receiving, some of the satellite dishes, which are only receiving, I can detect them and they harm me. So I'm suspecting that the satellite, you know, it's reflecting. I don't understand, but I just know that there's something real in the environment and it's a problem.
Definitely have to consider that. You had a question, sir?
When do you guys graduate?
1 week.
When
Next
should you
Saturday.
finish it?
The current tax
If I might speak to that for just a moment, I have 5 new students, okay, and to replace these 3, we got 5, which is a good thing, okay, and we're working right now, the pipe, the stanchion, is either complete or almost complete. The elevation mount is about to go out to the shop to be welded and machined, okay? And then the last piece that we'll be building, they ordered the materials to be cut for the counterbalance, which they call the triangle, but I call it the counterbalance. So my priority this fall is going to be getting that pipe mounted at the park, working with Carrie and the astronomy place and the new students.
What challenges do they face? Sounds like these guys did all the hard work.
So yeah, they also have to design and build. So one of the things that they did is they went back and looked at the designs that they did. There are some small modifications to these designs, and they're ongoing as we move forward.
What do you think your pointing accuracy is going to be from the mechanical point of view? In other words, repeatability and slop with the gears.
We had talked about 1/10 of a degree with the encoders.
Yeah, it'll be pretty good. We have an encoder right after the backlash, so we'll be able to tell absolute location of the actual pipe.
That's why I asked the question the way I did, in terms of mechanical stability and slop in the gears, not what the encoder shows.
Oh, through mechanical? Oh, okay.
The encoders will detect the slop.
It will be whatever the backlash of the gear is, which is going to be probably, I mean, I don't know off the top of my head, because the slewing ring is adjustable backlash. So you can adjust that as fine as you want. So it'll be minimal. But the reason why we mitigated that by adding in an absolute encoder to the center of that is to avoid that problem. So the software will basically account for any discrepancies, and it will always be at the right location within the accuracy of the encoder itself. So there will always be backlash.
The encoders don't compensate for slop.
No, but the way the machines work is like, if there is slop, the software will travel an extra little bit to compensate for that. So that's, the encoder will verify that slop, and what will happen is the software will say, well, I need to go a little bit more, so the gear will turn that little bit more to.
The encoder reader is stationary, so if there's slop, the encoder, that will be recorded on the encoder.
Yeah.
Okay? So
Because there's no mechanical gears or anything else between the encoder and the parts you're moving.
Exactly.
Is that true?
Exactly.
Right.
I probably saw.
Yes.
I'm getting at the point where you wind up trying to use the encoder feedback to compensate for mechanical slop as, say, the wind changes. And
You can do that, yeah.
and you wind up oscillating within the gap of the slop.
Yeah, but like I said, that's an adjustable gap, so you can get it down to the point where it'll be negligible, to the point where you probably can set it in your software, a limit or a range to prevent it from moving if it's within a certain, negligible amount, so that you won't get that effect.
The gearing's also 500 to 1. You have a lot of control over it.
Yeah.
What's your mean width at your chosen frequency?
It's about 1 degree, 1.5 degrees.
Yeah, so a tenth of a degree is meaningless then.
1420?
14.
Just curious in general, specifically about this project in general, what about lightning protection?
That has been considered.
It will get hit.
Yeah, but that's not my point.
I think it's pretty tall.
answer is
It's pretty tall, I think
This guy has a
it would
question.
make use of him.
This is kind of mechanical design and motorized tracking, and this 50-inch diameter?
15
feet.
50 of diameter. And I don't know about the surface of the dish, but what's the target in the radio astronomy? What do you want to observe? What's the plan for that area?
Well, okay, so we have a spectroside receiver from Radio Astronomy Supplies. And our initial work will be to do solar work first. Then we'll eventually break into, looking at Sagittarius A. We want to see, since we can do spectral, we want to look at the Doppler shift on the arms. Again, it's a semi-research instrument, but the real mission behind this whole project is to do educational outreach. So the fact and you'll hear about this this afternoon when I talk about how this all came together, the fact that they said we were going to make this fully trackable and fully steerable, now we can start talking about pulsar work. And that's really intriguing to us, because for me, that's the holy grail for me, is that we can detect a pulsar. That's going to be really, really neat. But again, it's really to spin people up. It's amazing. Every time we have a public star watch, I'll have my IVT out, and I'm pitching radio astronomy while these guys are doing optical. And it's amazing the questions that come back, and we never heard of anybody even doing this kind of thing. So and we know from experience, there's a lot of optical, amateur observatories that don't do radio astronomy. And when they get their first exposure to it, it's a wow factor. And I suggest that when you have some free time, these guys put together an awesome poster that Todd and myself had gone to Gettysburg for a conference, and we had a poster time to show and brag about our project. So we put a lot of time in of the overview of the whole project, which it's hung on the wall out here now. So you'll hear more of my talk. Mine's more of the historical account of the whole project, including Eric's Sauter's science project, how we got this. Todd is going to talk more about the software development and the real mission behind the whole project. So you'll get part 2 this afternoon, but that's basically what we want to do, Chip, is to get the word out and get people on board as to what radio astronomy is all about, and to have fun with it. It's the whole idea.
What size concrete block did you use to mount the post?
It's a 10 foot by 10 foot slab base foundation. 10 foot by 10 foot slab base foundation buried in the ground with a pier.
Rebar enforced, yeah.
It'd be pretty big.
Is there any opportunity for SARA to be involved in this project and perhaps contribute?
Yes.
Absolutely.
The answer is yes.
Yes.
Absolutely. We were real excited when you said, so Skip said he wanted to be involved with that.
Oh,
Immediately,
well, Skip's
got
doing
me.
it, we don't need to.
Well, he's part of
Yeah, because
SARA.
he has all the money since he's not, no, he doesn't have the money, that's right, you're donating it all.
No, we have the money.
You have the money.
But anybody else that wants to be involved, please, before I leave, let's make the contacts.
Yeah.
The 5 new victims will be here next year.
That's the plan. The plan next year is to come and brag about about all the great work that
That we're up
Terry's
and
doing
running.
with pulsars. So we'll see.
I don't think we'll be ready for pulsars, but we expect that first slate in May or June.
Yeah.
2020. Excellent.
Pretty awesome, guys, pretty awesome.
Thanks, Jeff. Lunch is happening soon, very soon, like now, but we've had a kind of a major schedule change. It's probably good. Tomorrow, we plan to visit the GBT 2 days in a row. Well, Mr. Murphy got involved, and they're not using, the GBT's doing astronomy work on Wednesday. So Sue Ann, our gracious host, wants everybody to tour the GBT tomorrow from 10 to 12:30. So we'll come in, we'll have Charles Osborne's Air Seaboat presentation, and then at 10, we can grab cookies on the way out, and there'll be buses for us. So the best plans, ice and men go messed up. So tomorrow, 10 to 12:30.
There's no slots.
Yes, there's enough slots for everybody to have a bunch of extra people. We'll probably have to gang up and get a little bit.
It's amazing. It's like one of those things you have to do.
That's it. Lunch.
Either way, I have
Anyway, so no problem. All right, I'm gonna have your.
The original, because obviously, look around the field.